and our third guest speaker, Cliff Click. I've known Cliff since he joined Sun in 1997. Yes, indeed. This audience might be too young for this reference, but how many of you are familiar with the TV show, or better yet, the movie MASH? Anyone remember the premise of the movie? No? So at the beginning of the movie, some high-ranking general in a field station in Korea gets sick, and the local doctors can't cure him. And so they send for this crack surgical team who are flown in from, I think, Japan to fix some problem, and then they get tracked there. Well, when I first met Cliff, he and his two other crack compiler guys had just been flown in from Rice. Yeah. Because we needed a fast compiler, and it wasn't clear that there was anyone who could do that. So these guys came in and they spent 2 years, I think, building what was an amazing compiler at the time, and still is an amazing compiler, I think, in its longevity and its performance. That's definitely one of the sharpest guys I've ever met. He's written lots of good stuff. He knows an immense amount of stuff. He'll give some of his distilled experience today, and you've hopefully read some of his papers and have good questions for him. So without further ado.
Thanks. So this is some facts about me real quick. The thing I'm most proud of is this one. When I went into Hotspot, it was widely considered that you couldn't JIT code. The word JIT even wasn't around then. Making code at runtime was just like it was going to be too slow and too low performance. It would never work. Especially doing like a heavyweight compiler, which is what I headed straight for. And I was roundly told by senior people all around the industry this can't be done. And of course, being who I am, I just took that as oh yeah. I get told lots of times you can't do that. Usually on stuff I'm already doing. So it's just I just blew it off and charged ahead, and it all worked out great. And so just to give you an idea, if you kick off a Java virtual machine, there's probably sort of 1,000 compiles happen by the time you do anything interesting. And if it runs for any length of time, there's between 10,000 and 100,000 compiles happening. If the average developer launches a JVM 100 times a day, then that's 100 times 10,000, about 1 million compiles a day. There's 1 million programmers in Java, and that's way conservative. Then there's about 1 trillion invocations of my compiler daily, just in the developer community alone. I've done all kinds of stuff, not just building VMs, so that's been a long time doing that. But I was doing compilers when I was 15, distributed computation in my 20s, early 20s, custom hardware, low latency GCs, non-blocking algorithms, lots of patents, lots of talks. Cool. Okay, so I've been working on Hotspot for a long time. This is a talk about virtual machines in general, but it's obviously targeted from my experience in Hotspot. But I have a lot of things to say here that I think apply to virtual machines everywhere. In particular, I've been in good contact with some of the JavaScript people, and less good contact with people at Go and Dart, who I'm watching make mistakes that I've made and have tried to tell them, and they're making it anyhow, and then they fail. And okay, fine. So there's lots of fun stuff in here. During the 20 years I've been working on Hotspot, I watched it become thread robust. And when I say thread robust, I mean it is reasonable and common for a VM to launch between 1,000 and 100,000 runnable threads, not just block, but actual runnable threads, and the VM will not choke on anything. It will run them well, run them efficiently. So that's the difference between like I can run one thread versus I can run 100 threads, I can launch threads. Getting 100 launched threads that actually run efficiently and don't choke on internal locks is a big thing to do. Hotspot can do it on the 100,000 level. I've ported it to half a dozen machines. I watched Hotspot pick up a bunch of compilers. I was very personally responsible for that one, which is the one that sort of shook up how people thought about JITting code. I had an offhand help in all kinds of GCs because I was always involved in how the GC interacted with JITted code. It's a key trick to make GC work at all in these systems is that boundary between GC and code. And a bunch of other fun stuff came in along the way. So the nature of this talk is there's just too much stuff to say. I've been doing this for a long time, and I'm fast, I'm furious, I code hugely, and along the way I've fallen in every possible pothole on the planet and picked myself and moved on. And so I can try to explain some of them, and I'll make my best effort at it, but there's just too much stuff. So many of the topics I'm going to talk about today, if you're headed for sort of the ultimate in speed or the ultimate in footprint or power or whatever, you get all kinds of engineering complexity and cost, but often these things also interlock badly in ways that are not obvious. And the decision that you made, you may not even realize you made it, will totally prevent you from going to the next level of power limitations or performance or whatever you're going to do. So, I'll say what I can, and there's lots more behind whatever I say. I'm happy to stop for questions. In particular, I talk fast, I talk furiously. If you want to find something out, ask, and I'll stop and answer it. And if you're confused so as the next person, that's all good. It's all fine to ask me. I'll take questions. So I'm going to start in with some choices people get to make. So VMs are generally considered these big, complicated beasties, or maybe not. Maybe they're really small things, like Squawk and OVM, a bunch of those little tiny VMs that do the job of a virtual machine in both a simple and sort of feature miniaturized way. But what features you find, how complex things get, depend on the features that you're headed for here. And so I went the big desktop server route, which is a very different set of choices from what I call cell phone guys. People who are doing systems for which the code is known ahead of time, what it's going to be. It may not be all in your native, in your virtual language. You're going to have things to run the radio on your phone, things, DSP chips to parse analog signals. You're going to have bitlet routines for your graphics screens and stuff like that. That's probably not in your virtual language, but you have to interact with them. And whether or not you do sort of arbitrary code here, and it drives an entire set of decisions on how the VM is implemented. I get my cord to quit messing with me here. So there's lots of other choices here. Are you multi-core? Are you single-core? Are you multi-threaded? Are you single-threaded? It goes on and on. Oh, here we go. So portable or not? Are you going to port to x86? It's the obvious choice. You're going to port to ARM chips? They're pretty common too. How about DSPs? Are you doing GPUs? Right? Okay. What about how are you going to call native code versus your JIT code? Use the same calling convention for them both. On x86, there are probably 4 or 5 commonly used calling conventions. You probably only want to pick one. And if you're talking to code that's in a different one, you're going to get screwed up. You have to fix that. You have endianness problems. Your x86, you're small. If you're ARM, you're big, or maybe there's a bit flip. You're going to do GPU, you're probably big endian. So you have to choose pretty quick what endianness you're going to be, because it's going to change how you talk about all kinds of things. Are your threads green threads? Are they, user mode threads, OS threads? Which way do your stacks go? They go, this way, right? Which way are they growing? Are you interested in small footprint or server route? These numbers are probably a little stale now. Are you going to have an interpreter or a JIT or no interpreter at all? You're going to be multi-threaded or single-threaded. There are interesting problems in the world for which people truly intend to write single-threaded code, doing all kinds of control language stuff for small machines for which they want a VM under the hood to make it easier to write the code. Your car probably has 20 or 30 CPUs in it. Probably many of them have a 4th interpreter buried in the bottom to get them up and running. That 4th interpreter is a mini virtual machine that lets it easier to just initialize hardware and screw with it before they launch onto whatever the main piece is doing. Are you multi-core? Are you multi-CPU? You have another new set of problems to look at. So let's look at some of the interpreter choices. There's somebody who was talking about launch doing hotspot interpreter. Right away he was faced with, do I do it in C or assembly? A simple, pure C interpreter is easy to write, easy to get started with. You'll spend all your time in dispatch. So you go to GCC label bars, you get about 2x faster than a standard pure C interpreter. But you go to assembly, you get about 2x faster again. Since there's a lot of run-once code in the world, there's a lot of startup code, it's actually worth it at some point to burn some cycles on the interpreter and have it perform reasonably well. I've seen a couple different ways to work on that dispatch overhead. That's typically half the time an interpreter's dispatch. There's lots of fun games you can play there. You can burn a long time trying to get your interpreter to go faster. However, an interpreter for Java means you have a stack-oriented layout, which sucks for JITs, because they like to do classic function call layouts where you have fixed stack frames. And the difference between a variable stack frame and a fixed stack frame for the interpreter versus the JIT code has to be bridged by implementation here. So maybe you give up on an interpreter. You can have none, and then you want to do something to run. So the obvious one should be stage 0 template-style JIT. Read a bytecode, slap some code out. Read a bytecode, slap machine code. Read a bytecode, slap machine code. It's very quick. It's very easy to generate. It's sucky code, but it's faster than the interpreter. except that the cost of getting it in the first place beats just true run-once code. Maybe you want to have stage one, I'll call it. Light optimizations, constant folding, dead code elimination, maybe some loop invariant hosting, and a linear scan allocator. And then C2, the one that I did for Sun, has like all the bells and whistles possible in it, including a graph coding allocator, every kind of loop optimization on the planet. This is a much heavier weight operation, but it gives you performance that's actually on par with C code, and that's easy to verify. You can write code that's faster in either language than the other one, but if you write straightforward-looking C-like code in Java, you'll get straightforward C-like performance out of Java. Do you care who you target? If you're, Oracle and you're targeting Spark, then you're going to make a Spark implementation. But most people do x86 or probably ARM. Are you having an interpreter? As I mentioned, it is faster for run-once code and startup code to have an interpreter over stage 0 JIT. But then you have to go back and forth. You have to deal with calling conventions across the boundary between interpreted and JITted code. And this final hook I'll talk about some more in a minute. This has to do with ultimate peak performance. In Java, methods are not final unless you ask for it. So by default, they're not. They can be overloaded. Typically, they are not. Inlining is the performance optimization we have. I'll talk more about that later as well. But if you inline a method and later it gets overloaded, you have to unwind and go back and try again. And the ability to unwind and go back is crucial to allow you to inline those non-final methods sort of ultimately and get that performance out. But that impacts your JIT very directly in how it tracks what it inlined, where those bits went. So stage 0 JIT versus the no interpreter model. This is this model where you just spit out code for every bytecode you run across and then execute it immediately. You see a bytecode you've not JITted before, you JIT it, you run it, you follow up the end of that little snippet you wrote, you run the next bytecode, you JIT, and you go. If you go backwards, you go back to some code you wrote already, and you run code you've already run, and that's the good mode. The problem, of course, is that it's still slower than interpreting run-once code, and there's a lot of run-once code to start up. There's like 1 million bytecodes for you hit main in Java. Good news for stage 0 JIT, there's no funny stack layouts. It's fixed size stack frames for everybody. Intercalls nicely with higher level optimization. You do get lots of bulky code at startup, big footprint, but you can throw away and regenerate it pretty cheaply. It's as fast to spit this code out in your L1 cache and cache miss it into your L1I cache as it is to suck it off the main memory. You don't even bother wanting it to go out to main memory. You just want to throw it away and actually write it out of your caches. Okay, let's switch threads here. GCs. Get started, use something simple. As you said, what was that, mark sweep or compacting?
They're doing a semi-space.
Semi-space collector, yeah. Something really simple. Stop the world, pick all your objects up, move them, shovel them, drop them back down. You want to go faster? Suppose you got a 32-core server. You got 32 cores producing garbage. You get 1 core collecting it. Okay, you're going to spend all your time collecting. Right? You got to go fast to keep up with the guys producing garbage fast, so you need a parallel collector. Or does fast mean low pause time? Are you interested in web services where you have pause times on the order of seconds, or somebody gets pissed and says, "Oh my God, the website's down. I'm going to eBay from Amazon." Or maybe it's low pause time because I'm doing credit card transactions and I have about 100 milliseconds between when the network transaction comes over from you're sending a line to Starbucks. I talked to a bank, between all the DB lookups and the overhead of sending packets around, about 100 milliseconds to make that call about whether I'm going to reject the credit card or not. So that means I want a low pause collector. Then maybe low pause is high frequency trading. I've talked to 20 different high frequency trading houses. Low pause for them means microseconds. They'd rather be nanos than can get it.
You mean latency, right?
Latency, yeah, low pause, latency. What is the max latency between doing this to doing that? Can I group all my GCs to a different point in time? I've totally talked to people who have arranged it that they only do young gen collections until the end of the day, and then they don't do a full GC, they just turn the box off and turn it back on again. How about exact collector versus a conservative one? Exact collectors allow you to move objects. That in turn allows you to compact objects, defragment your heap, let you do bulk pointer allocation easily and efficiently. That combination of compaction and bulk pointer allocation is worth about 5% to 10% performance over a conservative collector, which doesn't get to move objects. And that's because all your live objects, which keep shifting over time as what they are, get smeared out through your heap as a 90% drop-off rate. GC works because there's a generational assumption works. Most objects die young. The ones who live long, that use a lot, get scattered throughout the heap with dead stuff in between them. You compact, they live nicely in your caches. Because they're living nicely in your caches, you get better cache behavior out of them, you run faster. So it's a well seen in academic literature, people have measured this, there's a real effort there. Going parallel is hard. You get into all the parallel madness and low frequency race condition bugs, and concurrent. And both parallel and concurrent is really hard. And that's a problem that's sort of, I'll claim Azul's got it right, Azul Systems GC got it right, and no one else has got it as right as Azul does by like a fair amount. And it's a problem that people have thrown, probably thousands of man years at. I mean, how many man years has Oracle and Sun thrown at like CMS and G1? I mean, teams of 10 people, 20 people for a decade, right? And then IBM done the same thing.
Of that order.
And other people have done as well. So it's a hard problem. Okay, more GC choices. The two places that you're going to pick up stack roots, stop anywhere and save points are these sort of two competing things. I can argue well for them both, but I like save points better. What it really means is that in my multi-threaded program, this guy's running some hot BLAS loop, copying something from here to there, Saxby, I don't know what the hell he's doing. This guy wants an allocation, the heap's full, he's out, has to do a GC cycle. He's blocked until GC happens. This guy's in the middle of running code. You gotta stop him, because you're gonna move the array that he's working on in your moving collector, and tell him his pointer's moved. Okay, where does he stop? How do you stop him? You go to the OS and say, stop that guy. The OS stops that thread. Okay, his piece is in some random place. Now you wanna move him, you wanna go fill his registers with new places, right? Where the objects all, bases all move to. So you have to go find all those registers that hold pointers. And how do you do that? Well, one way is to have a map at each program counterpoint, but that's very bulky, and actually changes kind of modestly by instruction. So people often will have tried at least doing things where they have loop maps periodically, and you interpret instructions between loop maps as a sort of a way to compress the data down. And so you start at some point nearby, and you walk forward counting instructions, modifying the loop map as you go to get the one that you're at, and you say, well, this is what my pointers look like. You do other games. Fix your oops in the registers and stack areas, maybe even odds. The evens hold oops, and the odds do not. And then I don't care, I just say evens and odds, and I spin more that way, and I can find all my pointers. I've seen JavaScript guys say I want to be conservative on the stack and exact on the heap. And the observation there is exact on the heap is sort of easy to follow because those roots are fixed and unchanging and sort of relatively easy to track. And the stack roots are hard to track because they're changing very fast according to how the JIT code's running. But in a 64-bit pointer land, there's not so many ints that will falsely be confused with a pointer. So even though it's conservative, it's not very conservative. The downside, of course, you still can't move things that are pointed at by stack roots. And exactly those are the guys that are hot that you want to compact and you want to move. Save points are places in the code where you have arranged to have a loop map, and you want the guy to have stop there. And the way to do that, for instance, is to pull. So some JITted code you wrote that said, load a bit, test it. If it's not 0, I need to stop now. And you're stopping at a save point. Azul did it in hardware because we thought the cost might be high. Turns out on x86 it's essentially free. You can be preempted at not a save point, same as the stop anywhere. The OS might just preempt you because it does. And then if you want to get to a save point afterwards, you might have to roll forward somehow. So imagine you've got 100,000 runnables. The OS is running 32 and 32 cores, and the other 9,999 whatever, they're all asleep somewhere. They've all been swapped out. They're all at some random odd address in code. Now you want to do a GC cycle. Well, the bulk of them are not at a save point, and so the bulk of them all have to be woken up by the OS, run forward a little way, stop at a save point, go back to sleep again as you roll forward 32 at a time on your 10,000 to go, right? So that will take you a very long GC pause, whereas if you could do something cooperative with the OS, you can get them to stop at save points ahead of time and make life a lot easier. So speaking of multiple threads, so the multi-threading costs. So if you're landing in the realm of one core, you don't need locking. As soon as you go to multiple threads, you need some sort of locking mechanism, lest you get preempted while you're holding onto some or manipulating some critical resource. So you have to go find all the places where you need locks. That's actually a hard problem. As the program gets bigger and more complicated, the number of places and times you need locking sort of scales up and becomes very difficult to find because you get low frequency bugs. You do need the stack pointer in the program counter to find your stack roots, which you would normally ask an OS for. I stopped that thread because I wanted to do a GC cycle. Give me his program counter. Well, it turns out, common problem with OSs is that with low frequency, most OSs that we would consider to be robust will lie. Hand you a garbage program counter, garbage stack pointer back. That led to any number of long-term, difficult-to-find bugs in any number of VMs that I worked on. And the reasons were all kinds of races deep in the OS, between hardware races where the hardware was caching registers, in hardware-only spaces that it didn't tell you what it looked like, and they varied from chip to chip, to games like this where you've overflowed and you're trying to throw a stack overflow exception, and you took a TLB miss and the overflow handler, which went to a page fault, and deep God knows where in the OS somebody returned the wrong one of these, and the pointer didn't get moved for your stack overflow exception object, and then you crash and burn later. How about multiple CPUs? So not just multiple threads on one core, but multiple CPUs. So now you need actual atomic operations, not just locks. To implement a lock here, you actually have to have a true CAS operation, CAS instruction, piece of hardware. You have to deal with coherency and memory fences. You have to deal with some sort of low-frequency data race bugs where multiple threads, multiple cores are talking through memory in ways that you're not expecting. You have to deal with scalable locks. So before you need locks on your one core, but it just meant you switched the thread to a different one. When you have lots of cores trying to beat on a lock, they need to compete well. Meaning you can't spend all your time waking up and going back to sleep. You've got 100,000 guys, and you wake them all up, and one guy grabs the lock, the 999,000 have to go back to sleep. And you spend all your time in your OS, waking them up, putting them to sleep, waking them up, putting them to sleep. So you got to do something about scalable here. And you have to do scalable locks in digited code as well. So it's not just that you're implementing locks in the language implementation, you guys are writing your VMs in C or C++ or whatever. No, you have to legit scalable locks. So that's a real hard trick, including games like spinning and retries for lightweight contented locks. And under super high contention, you must have fair locks. All modern, large Java app servers, web servers, whatever, expect fair locks. They're not demanded by the spec. But if you don't implement fair locks, when their thread count exceeds some amount and some big load hits it, some poor thread will be totally starved by the OS, and I can show this on every OS on the planet. That starved thread waiting to acquire a lock will never run until his timeouts happen. Then the VM will start throwing aborted transactions left and right, and it will just go down in flames, as an app server kind of thing. These guys all rely on Hotspot doing fair locks under super high contention. Other games, a thread might wake up, lost in, preempted out, or lost in native code, getting his network packet arrived. He wakes up and wants to process the network packet. GC might be in progress, might be mutating his stack. You can't actually touch his stack. In particular, on like Spark, you can't have a Spark register window prefetch stack elements that you're busy trying to write with the garbage collector. You need to take some sort of GC lock over your run. But this is a little bit of a lower level, nitpicky, fun game. The original implementation of 64-bit math and Hotspot was as a pair of ints with a carry. You loaded the load two, you added them, you pull the carry out, you throw it in a three input adder to get your 64-bit add. Turns out that the big user of 64-bit math is a big integer package, which is called by crypto every time somebody does a web service with a encrypted transaction. Big integer actually uses longs like they're a pair of ints. They shift to left, they shift to right, they mask the high, they mask the low, they want this bit or that half, and they're trying to do merging to carry the propagation around. So it turned out that it optimizes really well as a pair of ints. All those masks and shifts at the Java level turn into simple register selection at the x86 level. I grabbed these 4 bytes from memory, and not the whole 8 bytes and then shifted it. No, I just grabbed the correct set. Better code by far on an x86 or an EMI32 machine. And it took a long time to get the 64-bit instructions to actually look and work as well as the 32-bit instructions. It needed like dual issue on the 64-bit ops as well because of the masking and the shifting was extra ops that had to happen that you didn't need when you had it broken in half. So there was a transition Hotspot went through when it used to do this version of math, and then it went to 64-bit math and didn't understand how to do the add with carry trick anymore. And actually the code got worse for a while. It took a while to get back to the same performance. Okay. What was my wild romp through things that weren't obviously choices when I started out that in hindsight were like, oh shit. We made a choice here and now we're kind of stuck. All right, I'm going to take a deep dive into native calls, which sound like a thing that ought to be really easy to do, and in practice turn out to be really, really hard to do, and have some hard lessons in there. Okay, So I'm going to show this for Spark because that's the time frame when I wrote the slide. But the same game happens on x86. And really the idea here is that I want to call some native routine. Like I want to blitz some stupid piece of pile of bits onto my screen to make a pretty, log in me now, click here button, or whatever the hell it is. And if I have a fixed application set, like I own both sides of the equation, I own the Java code I'm running and the JVM, and I own the native code I'm calling, then this problem goes away. I can do the right things very, very trivially, and do the obvious thing. I just make a call, and it works. And because I know what the native code's going to do. If I don't know what the native code's going to do, then my life gets a lot harder. So I'm going to show this example here. I'm going to start by saying, register window push on Spark, and on x86 you'd add the BP. Make a frame. Oh, the incoming R is probably in the wrong register. You're going to move it. No big deal. Take your native call. Your return result hopefully is in the right register on x86. It wouldn't be that one. Pop BP, return. Pretty standard stuff. Well, actually no. So if you're on, well-strung type language, you probably know where your float values are. They're in float registers. And your ints are in the int registers. And there the twain should cross. Except C compilers for the longest time do vars for printf purposes, and all the floats have to be passed in the int registers. So in the beginning, when you made your calling convention choice, did you choose to do the native x86 calling convention? If you did, you get to skip this step. If you did not, you skip this step, and instead, every time Java called Java with floats, you shuffled the R's to the int registers, and when you got into that routine, you shuffled them back to the float registers to do something floaty with them. Right? So this is in the wrong place. So now you have to decide where you're going to pay the cost. Java calls Java or Java calls native? What's more common? Well, Java calls Java is more common. So put the floats in float registers. Therefore, when you make a native call, they're in the wrong place. You got to move. In this case, because it's a 32-bit machine and I'm floating a double precision, I have to move it through memory and two different registers because it was 64 on one side and 32 on the other. Would go away if you're a 64-bit x86 or not these days. But you want some way to do a fast argument shuffle. In general, the trick is a parallel copy from this pile of registers to that pile of registers, where registers include stack slots because you had more things being passed than fit in registers, so something just spilled on the stack. And the guy you're calling wants things spilled into different places on his stack. So you have to do some sort of horrible shuffle, which is really just a bunch of loads and stores, register moves. Still got to generate them, solve that problem. Okay, next thing. Can't pass garbage collected pointers to native code, because the native code won't tell you where those pointers are.
Back on argument handling, I was wondering, you said earlier that there are a ton of different argument calling conventions.
Yeah.
And the world would not grind to a stop if you created one more. Why did you choose to, or why did Java choose to adapt to all of these rather than have the world adapt to it?
No, well, because Java wasn't important when I started out.
Yeah, it's 2016.
C code was everywhere, Java was nowhere,
Yeah.
right? So I had to choose to have the C calling convention, of which there was a 32-bit one, and the 64-bit one wasn't around yet, of which there were several 32-bit ones, but there was one that was more common that Intel was pushing. And then, what I do with floats when I'm strongly typed as a language, I know damn well where my floats are, whereas C code did not.
But, as an example, did they have the Java memory model on
No.
day one?
Nope.
Okay, so they eventually learned and they decided that they needed.
Yeah, and in fact, the first cut of the memory model was entirely flawed, broken in a lot of ways, and I ended up implementing I did the reference implementation of the second cut, and I went back and forth with the guys designing it as to what could and could not be done in a compiler, and what it meant to do the memory model. So totally, there was no memory model in the beginning. So C code doesn't have a memory model, so right away you get this funny game of, I called C code, what did it do? Well, the answer is, you don't know, because the C compiler didn't know, because there was no spec, right? So you had to do it on a case-by-case basis. This compiler emitted this code in this way, therefore I can guess, what the hell, but there's no way to upfront a priori define for a particular C code how it's going to behave in a multi-threaded environment. You can only say, for this compiler, this web of this compiler even, this is the code it emitted, I now know what it does. It was a long time for x86 gave us a memory model, right? For a long time they delivered chips and not motherboards. But the memory model was all about how chips communicated through the motherboard, which they weren't making. So they refused to put out a memory model, and you had different memory model behaviors where you had a compact dual core versus Dell or Alpha or who else. There were a couple people doing dual core machines back then. They varied. We got kind of fun bugs from those games that were up to the motherboard, and Intel threw their hands up and said no. Fine. Everyone read this slide 5 times over? I need to pass in a handle because the C compiler won't track my pointers. To this day, they don't. LLVM, the common other C compiler out there, is not got pointer tracking built into it in this way. So if you build native code and you're passing oops in, he does something with that pointer, you don't know what. If you want to move it later, because your GC says I need to move it now, then you can't find it in the JIT code, in the C compiler code, and fix it there, right? So you don't let him have it by giving him a handle instead. Give him a pointer to a pointer. So you build a pointer to a pointer. Null is the handle for null, otherwise you put the actual oop in the stack, flag this with metadata, there's a pointer here, you hand the address to it. And you unwind when you return the pointer by asking is null, if not, you have to dehandle it. Might need locking if you're a lock native. Here's some locking code. Load the header word. This is a thin lock, so you set a bit, you attempt to cas it down. If you succeed, you win. If you lose, you go to some slow path that's out of line. When you're done, you have to unlock. Again, there's a slow path in case you need to wake up some guy. You have to do a notify that you let the lock go and wake up some guy. All this code is getting jitted every time I'm writing a call to a native method, of which there'll be thousands and thousands of these things. Right? Okay, I have to allow stack crawl. That means on entry to the native code, which might block. I don't know how long it's going to be. Like, this is not a problem if I know what the hell the code is doing. I'm doing some bitlet to the screen. It'll be back in a millisecond. I don't need to allow for a GC during that millisecond. Okay, I'm calling to native code. I don't know what the hell it does. Maybe it's gone for the next millennia. It's waiting for the disk to come back. I don't know. So I have to allow a GC while I'm waiting, right? So how do I do that? Well, I have to slap down. As I mentioned, I don't have the OS and the program counter reliably from the OS. So I'm going to slap down the program counter and the stack pointer beforehand. I'll put them in some low thread level storage area. Here, do it this way. In x86, the answer is a little bit different. Get thread level storage in a couple ops, in x86 a different way. But I slap these things down. And here, I'm relying on, this is Spark hardware memory model. x86 is a similarly conservative model here. This store instruction is the unlock for the GC lock, which is like an inverted lock. When all threads have let it go, GC is allowed to claim it. If they have claimed the GC lock, then they own the heap and they can mutate it. No running thread is allowed to then peek at his own stack, because GC is about to edit his brains, or he's doing brain surgery on himself, right? So this instruction will turn GC on at that clock cycle. This is the funny thing about race conditions and code here. This instruction has to be coherent in memory for the GC thread to find it at the time that this instruction happens. These two stores cannot be out of order on my big, fat, wide-ass 3200-way machine, or else I have a low-frequency bug where GC will grab this, see the stack's available, lock it, grab this, get the wrong value, crawl the wrong stack place, crash and burn. So already I'm deep into memory models. Well, I'm just trying to say, I want to make a native call. There is a very delicate memory model dance going on here with a racing GC thread. Having done that, I have to unlock and way out, which does the same thing in reverse. Go grab, this is, the instructions are different on x86 because the CAS takes different ops, but basically I slap down a 0 saying, I want to CAS down a 0 saying, hey, you can't GC me anymore, I'm going to replace my program counter with a 0. If I succeed, I own the GC lock on my own stack, I can get to mutate my own stack, I can read my own stack. Until I acquire it, I cannot read my stack. In, for instance, hardware peek ahead registers, which, you know, like register window machines will like pre-grab the next set, they can't, you're not allowed to. Because the GC is still like probing the updated bits into the stack. So it's essentially, it's a lock acquire. A couple other odds and ends for Dollyland. I need a JNI in environment for the standard JNI handler wrapper crap. As a service for native code, we allow handles beyond some local stack, so it's cheap to allocate and throw away bunches of handles. And we reset the handle before and after making a native call. So the native call is allowed to make more handles. He's handing handles, he wants to make more. And then at the end of the native call, you can wipe them out quickly. So this is what it looks like. There's some, oh, I made a stack frame, I look at my JNIM, I'm handleizing however many oops I got passed in. I had to do an arg shuffle, get my floats in the right place. I have to enable my stack to get called. I have to do my GC lock, make my AF call. Sort of like a, the least little thing. And then I have to unlock my GC when I come out and allow, well, I'm racing against the GC, see if I can mutate my own stack, dehandleize, and clean up and get out. So I went from, 3 or 4 clock cycles and a couple instructions to, I don't know, 50 odd, not counting, there's more if you have more arguments, more if you have to do locking kind of games here, and a lot of clock cycles. And that's, the difference here is that this is required because I don't know what the hell I'm calling. It could block, it could come back right away. It could do bad things to pointers. It could try to hang on to a pointer that I want to move later, and I can't let them do that, or I'll just get a low frequency crash at some future date. So there's lots of defensive things happening here because I don't know what the hell I'm calling. Okay. All right, we'll switch here. So here's a collection of things that we did, that going in, we didn't know what the hell we were doing, so you just make a guess. Best guess at the time. Oh, this way! And you take off and you go. You have to make something happen. And then it turned out to work well. So safe points worked out really well. Turns out that it was a great notion for letting threads do a lot of self-service tasks. I'll talk more about that in a minute. It was a great spot to do de-optimization. That's that unwind from over-aggressive optimization, usually over-aggressive inlining. Inlining being the performance optimization you wanted to inline furiously, as much as possible. And then occasionally make a mistake and back out. Backing out exactly required a lot of state to get tracked by the JIT. Tracking that state would generate necessarily code to be able to unwind your state back to the Java virtual machine architected state. Turned out having these safe points around led for good optimization of that unwind state. Typically, you had to hold on to a few variables, otherwise be dead. Typically, the virtual allocator would spill them off to the stack and mark them. And then that was it. That was your cost to maintain a safe point. At the safe point, there'd be a map saying, oh, you wanted a Java virtual machine local 1, 2, 3, 4, 5, whether here, 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 and here, spilled to the stack somewhere. The JIT code didn't actually want them, didn't care for them. He just spilled them out to hang on to them. So it led for good optimization, good performance, and the ability to stop at any point and unwind. Self-service tasks, things like find your stack roots. Well, it's all hot in your own L1, right? Your thread's doing it himself. So he's running through his code, screwing around with the stack, test the bit. Oh, safe point. Crawl my own stack, collect all the roots. Maybe flip them all, which is GC faceflip. Slap them down somewhere in a buffer for a GC thread to find it, and go on. All over with in a microsecond. And that's, GC pause time on that thread was a microsecond, maybe to crawl, a couple hundred K of stack and find all the stack roots. Polling turned out to be really cheap. It's a load compare branch. The load's hot in L1. The branch is entirely predictable because you never ever stop at any given safe point. It's extremely rare. So it was really cheap to do this polling. Cooperative preemption was the thing we did with Azul, and that was to handle a case of 100,000 threads. The OS would just call into a thread and say, hey, your time slice is about up. I'm going to stop you at the end of 10 milliseconds. Stop yourself soon. And that thread would see the safe point bit, stop, and do a yield. And that was how I got all my 100,000 runnables to all be stopped at a safe point already. And that meant the GC in the background would be crawling all their stacks and mutating them while they were blocked by the OS without ever waking that thread up or looking at it at all. It would never care. GC would take his lock, crawl a stack, mutate it, and release his lock. That thread would never even know. Okay, another thing I did. Heavyweight compiler. This is the one that everyone told me you can't do this. But it was really necessary for peak performance. I routinely got into this argument with managers at Sun where they would say, oh my God, they're just too slow, we're spending all our time jitting and not running code and whatever. I said, well, I can make the jit go faster by turning off some optimizations, or I get more peak performance in all the benchmarks by putting in more optimizations. And they were like, oh, but it's too slow, but peak performance. Every time. So I went for peak performance. And then compiler got slower and slower and slower. Turned out it didn't really matter. It's still an extremely fast compiler for what it does. If you time it compared to a standard classic LLV and GCC thing, I'm like 100 times faster. It's hugely fast for what it does in terms of code optimizations. And it didn't matter. More and more CPUs started showing up. What the hell do you do with them? Well, most of the time, they're idle. They're blocked something, no one launched enough threads, what the hell? The JIT's running in the background. So why not burn some cycles to go make better code? I went with something I had worked out in grad school, graph-based intermediate representation, sort of very non-traditional, but it's also very fast, very lightweight. It was what made the compiler so much faster. It's very easy to extend, it's very easy to teach people. Once they got their head wrapped around it, it's a graph rewrite rule to do an optimization instead of a sort of a classic bit vector data flow problem. It's a very different mindset. But once you wrap your head around it, it's very easy to work with, manipulate. Graph culling register allocator, a key item, is that let me be robust in the face of over-inlining. So let me step you through the fail mode here. The problem people have had with register allocators in the past, especially linear scan ones, was that once you began spilling, one good spill deserved another. So if you inline and your method got larger, your effective method that you're jitting got larger, you inline some more and get bigger, more and more stuff gets live over longer and longer spans. Eventually you run out of registers, you have to spill. When you begin spilling, well, if one gets spilled deserves another, you end up spilling a lot. These things have a knee in their performance curve. More inlining meant you ran faster because you got rid of the call overhead, you got to optimize across the call boundaries, until you began over-allocating, or you over-inlining, and you spilled and spilled and spilled, then your performance fell off. Bam. So to stay away from that knee in the curve, they would throttle back the inlining some amount. So they were not at the peak performance because it was too fragile at peak performance, right? The fix is to make the allocator not fragile at over-inlining. So the cost of a not inline method is you save your call, you save registers, you make the call, you save your call or save registers, and you did your thing, and you unwound those. So you saved a bunch of registers on entry, and you loaded them back on exit. You had a bunch of spills, but they were split across the call boundary in the call prologue and epilogue code. So that was the hidden cost of not inlining for register spills. The trick is simply make the allocator do no worse than that. He's got that many instructions he can spill, and he's not doing anything worse. Once you get that right, then you can crank up inlining. You crank it up a lot. And it doesn't matter in terms of spilling, but performance would sort of asymptotically increase till you hit a point where more inlining really wasn't going to help you. You had where iCache spilling, there wasn't anything more to go get out of it. But not inlining was the fail. You must inline, and you must fix the allocator to deal with that.
What is it about a linear scan allocator that makes it do worse than the call boundary?
I don't know. It has a clear, like it doesn't do as well. It doesn't have as much global knowledge as a graph coding allocator for when it allocates. But there are two pieces to this problem. One is, how do you do an initial coloring, assuming you have enough registers to color them, if it was possible at all? And then when you fail, and always when you over inline, you must fail. And typically you have things locked into the wrong registers for coloring convention reasons anyhow. So there's a lot of spill code happens no matter what. Now, how do you turn that into not so much spill code? That's where I hadn't figured out why the linear scan guys never seem to do so well. I did some myself, and I watched other people do it, and then I flipped to graph coloring allocators while I was in grad school. Like, I did my first graph coloring early on in grad school, and kind of never looked back. Like, it was clearly better, sort of theoretically, when you would be able to color and the linear scan guys could not. And then I dealt with spilling after that, sort of how to make it friendly with graph coloring. The same techniques I did for spilling for linear scan, I talked to the linear scan guys, and they had other approaches. Linear scan allocators are much more approachable in the sense that the curve to get started, the learning curve to get started is lower, but I think it does peak out at a lower point because you don't have that global view that you get out of a graph coloring allocator. But here's a funny, this is like graph coloring knowledge for people who care. I don't know what anyone in this room does. First x86, right? We had 8 registers. Well, stack pointer's 1. You had 7 allocatable registers. So I had a 7 register machine to deal with. So if I went and did a graph coloring allocator and I looked at the average live range at the first allocation after all the inlining, the number of neighbors in your interferences in your interference graph was well past coloring, 15 to 30. The average was like way high. So you do a round of spilling. At one round of spilling, it would drop to an average of 8 out of 7 possible. And then if you're lucky, of course, that would just color right there. So the game there is that you always end up asymptotically approaching maximal colorability with a graph coloring allocator because your spiller does something, but he doesn't, if you don't just blatantly overspill, you underspill by a little bit. You didn't hit knowing ahead of time you're colorable, but you might be when you try it. But instead, you're always a little bit, not quite colorable theoretically, but in practice, it turns out you got colored pretty quick. And then you always got a much better allocation out of that. Whereas the linear scan guys would make a pass, know they had to change stuff, changed a bunch of shit, but then they didn't have any evidence that they were going to get better quickly. So in the next pass, they started spilling again, and they couldn't fit it all on the round 2. They had to throw up their hands and do something really aggressive about spilling. And so they would just spill like all kinds of things. And that would get them to be done allocating. Otherwise, they'd be, oh, another couple things didn't make it this go around. I'll have to spill some more things and try again. The 4th time through, they're like losing big time to me doing my 2 slow passes versus their 4 fast passes. It was like, they were losing ground and with it. So it was never as good, and I didn't fight hard enough on a linear scan guide to know why it was never as good. The experience was just never as good. Okay, other fun games. Portable stack manipulation code. In the beginning, we started on x86. We flipped to Spark, which had these fixed register windows. So it was a pain in the butt. The stacks went the wrong way, and each one went a different way. Where we had all this little code that we had to go mangle around with. Then somebody came up with this brilliant notion. I kind of needed a base and a next notion and an end of it notion, which is a frame iterator. It's just a plastic iterator. But it was written in C code, creating templates, whatever, and intended to crawl stack frames of low-level thread stack frames. Turned out to work for a wide range of CPUs and OSs. Worked pretty well with registered windows. Actually, Itanium, Azul, and Spark all have sort of fundamentally different register windowing models, and this seemed to cover them all very well. So it was a really great notion to extract out all these weird sort of machine-specific bits of what does your stack look like, and get into the notion of, here's my upper abstraction layers, I'm trying to do something intelligent with the stack, and the lower layer is just manipulating where you are and what the offsets were, went this way or went that way, finding an OOP, what it meant to take an OOP map, and which one, whatever. It was all covered under the hood. There was another notion I put on here, but I mentioned before, is that frame adapters is an idea of how you can mix JITting and interpreted code as well as linearizing call arguments. Interpreters having their variable stack layouts, an adapter was a way to change the stack with a little piece of machine code that would just shuffle the args around from what the interpreter expected to what the call site expected for the JIT code using the standard good calling convention for the JIT code. Both those things get into like games with manipulating your stack, which you have to get really, really comfortable with in playing these kinds of things. Code cache. We're still all happily living in 4 gigs of JIT code or less. We're not close to that boundary, which means you only need a 32-bit program counter, which means you can use a cheap local call instruction on x86 and on Spark and on RISC and on ARMS and everyone else. So you really badly want all your code to fit in 32 bits, and you crunch it all together and put it at a 4 gig boundary and say, this is my code cache, and nothing else lands outside this aligned 4 gig block, and then all my call instructions are all like this dirt cheap form. It's like big savings, actually. It really is. Fast and slow path stuff, blah, 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 like bugging flags. So as you saw in my native code callout, I had a lock slow fast path. I have a allocation fast slow path bailout. I have an instance of runtime cache check fast slow bailout. I have about 20 or 30 fast slow bailouts. If you're taking the slow path a lot, you lose. Slow path is slow, right? You don't want to take it. That's the whole point. You did this because the common case should be fast, but there's an uncommon case that has to work correctly, but it's going to be slow if you take it. Well, then how do you debug this code, which is by design infrequently executed? You have complicated, tricky code that's by design infrequently executed. How do you QA it? How do you debug it? Well, you force it to happen a lot. You turn on one of these flags, and whatever slow path thing that's gating here now happens all the time. It runs really slow. So you tell QA, hey, go turn this flag on. It's going to be 10 times slower. It's going to take overnight. I don't care. Come back with whatever bugs come out of crashes and burn. And usually it catches lots of bugs, usually in a very deterministic way. What turns is a low frequency, it rarely happens crash, happens like every time on an overnight run. And then from there you can begin to binary search your way down into what the hell is going on. That's Dave Unkelweiler. That was a good one from him. Fin locks. Bacon bits. Bacon bits is not a David Bacon. Fin locks is basically the Java notion that every object can be locked. But if you want to lock an object, there's some state you have to carry with that object that's dead weight otherwise. And since your heap is full of objects, if it's full of dead weight, then your caches are full of dead weight and everything's running slower and bigger and whatever. So you want to keep them as small as possible. So the thing we figured out was that you could get into just a single word in the object header, in fact, a fraction of that word, and you're going to have to do a CAS on the object header to say, I took this lock. And if you win it, you're all happy. And if you lose it, there's some slow path you're going to go deal with. Hey, I failed to get a lock. I'm probably going to go to sleep. Unlock was a lot cheaper now. Back in the day, every CAS was a missed main memory on x86, so go out to lunch while 300 clock cycles at a 4-wide issue machine, 1,000 instructions didn't happen when we took a CAS. These days, it's only an L2 hit. It's like 10 or 20 clock cycles, and the unlock's guaranteed to be in your L2, so it's much cheaper. But already at 20 clocks, you can do better. There's a lot of locks that are essentially never, ever change ownership. So you want to think a lock, respectively owned lock. No atomic locks other than the original take it. Once you take it, you just fail to unlock it. You leave it locked. Next time you go to acquire it, you already own it. And all you have to do is say, hey, do I own it? Oh, I do. No atomic operation. Atomic operations, including the x86 memory model, memory fence, that forces the hardware to stall until loads and stores settle out across that barrier the correct way. Not taking that fence lets you run faster. Furthermore, you cannot take that fence in the JIT code. Taking the lock at the beginning, knowing that you hold it all the way through, and all the inline synchronized methods, which have the locks and unlocks all the way through, throw all those out, including all their implied memory barriers. You own that lock for that whole time, whether you should have held it or not. Do what the hell you want in the JIT. Nice, tidy performance savings. Of course, pain in the neck to get it back if you're wrong and somebody else actually wanted it. So you have to do something. There's another good operation for safe pointing individual threads, is when one thread says, I want this lock, and this other thread says, well, I'm kind of holding onto it spitefully. I can't let it go because I actually don't know if I should hold it or not until I hit some safe point and inspect my state, discover if I really own it, or I'm just like hanging onto it. And so there's some engineering you had to do to make that work. The memory model, another thing that didn't start out there, as I mentioned, it came along later, but it worked out really well in practice. Major piece of programming, I don't know, it's a mindset or learning, whatever, that had to happen at that era, more than 10 years ago, that hadn't happened up till then, that suddenly made it possible for people to write multi-threaded code, by the millions. Prior to then, all those multi-core things, they were all handcrafted by guys doing, HPC, and all vary from hardware to hardware to hardware. And so every one of your multi-threaded programs that ran on the Cray, whatever, failed on the Fujitsu supercomputer, whatever, because the multi-threading core talk-to-talk thing was all wrong between the two. Okay. Yeah.
Can you just define what you mean by memory model? I just don't know what that word.
Oh, okay. So memory model is simply the rules by which two threads talk through memory. So the obvious example is this guy wants to fill an object and publish it. So he stores to fill the object, then he takes the pointer and he stores it in some global place to publish it. This thread wants to find that object if it's available, and if it's not, he probably makes his own one, but he does something. So he reaches for that pointer and he finds it. Then he reaches through the pointer to the place the other guys filled in the past and asks what is in the contents of that object. So if these stores are out of order, this guy will fetch the object, fetch through memory on the other side, and get garbage. Right? So this store and these loads, so there's a store and a load and a load. So always memory model implies there are two threads. It's never interesting to talk about one thread. Although people will say, oh, I got this in one thread. No, you have to talk about two threads. Okay, store, load, and did one of these cross, right? The memory model is telling you what the rules are for when that cross is allowed or not allowed to happen. The big one is you want loads to bypass stores to get this right. The thing that is hard, that is expensive to do, is have a load stall. Let's say it's a load bypassing store is the big one. Like stores, two stores are easy to direct in order. Two loads are harder, but can be done. Load store orderings, x86 will let you go out of order on in the hardware in a big way. And so in particular, if I store down to take a lock and then I load, I have to have a fence, or my load happened earlier than my store was visible around the cluster. So the store hit on my core, and then its speed of light sort of propagates out as people make coherency rules. My load happened to hit my L1 cache because I was lucky, so it happened right away. Okay, but I didn't actually own the lock yet from that guy's point of view because the store was still propagating. So that guy, having not did a load of his own, the store hadn't showed up yet, the lock's still open, he does something, and I got the wrong thing. Right? Okay. So there's a game you have to do there where the fix is you have to emit fence instructions to prevent bypass in a certain set of places, including in the JIT code. The JIT has to understand how the memory model works to know when he has to insert a fence in the code. Okay. Yeah, burning some brains out. Okay, things that were hard to do but worth doing. Making it portable. it turns out that it just gave a better discipline to the code. It separated out implementation from idea. Below the line, I'm talking about how stacks are laid out, whether they go left to right or right to left, whether they're big endian or little endian, if I have a register window to screw with or not, is my register window flushed or not, how it goes, how are program counters stored on the stack for return addresses, sometimes they're in different places, or not. And above the line, I'm walking through frames, and on this frame, I want to find out stack roots. I want to mutate all stack roots. I don't know where they landed in the stack other than have a map which somehow correlates to the actual bits in memory. The abstract layer doesn't want to know how that works. He just says, oh, my goal is to walk the stack and find the roots. My goal is to discover, do I own this lock or not, because I want to release it for somebody else's purposes, or whatever it's going to be. Middle compilation tier, a little bit of non-obviousness. Hotspot lived for a long time with an interpreter and either the client or the server compiler. But it turns out that the middle tier compiler, however it's done, you usually make it the fast version with the linear scan allocator or whatever the hell. If you put profiling counters in there, it can profile about 10 times faster than the interpreter can. So the code will run much faster than the interpreter code, but it can profile at much higher speeds than the interpreter can, and it can do it more precisely because he's done some modest amount of inlining, and then you get inline-specific counters. So when that heavyweight compiler kicks in, he gets a much higher quality profile to go drive his own compilation decisions. So it turns out it really is interesting to have a middle tier, and in particular, you should not bother to profile the interpreter other than the basic counts to say get to the next level up. But the next level up should profile everything on the planet and hand those profiles off to the next tier that follows. Dopt. This is this thing I was talking about before, with inlining finals. And you have to be careful here with jargon terms. Hotspot used Dopt for a particular word, but the academic literature went a different way with that word, so their meanings are subtly different. But if you're looking at Hotspot and how it does it, and 99% of the VMs on the planet are running Hotspot, you have to pay attention to what this actually means from Hotspot's point of view. So the real impact here is there's no runtime cost to inline non-final. Okay, and people who aren't playing this game pay this no hoisting cost at runtime. And what the hell does that mean? Well, it means there's a line in the sand in the code where the inlining was conceptually to have happened. The call went away, the instructions got inlined, and then they went down and smeared throughout and got merged with other code. In the Hotspot, that point went away entirely. It's not there at all. That inline code completely scattered in all directions. In particular, you go up, which you can't do in the other model. You can go up and merge with other things like you're inlining an accessor function that maybe gets overloaded later, but the accessor function is just a load. The load might get hoisted out of the register, might get common sub-expression with that same load done elsewhere. It definitely pays off. Of course, if you do override the code, you have to flip it to an interpreted frame, and that's not rocket science, but it is kind of hard to get it right. It's full of nitpicky details to do the Dopt in that way. And also, the other effect out of a lot of these guys is that they have a point in the sand where they went down. At the Dopt time, they patched here. They say, oops, you can't use this code because the overload changed. But then they forever paid some sort of cost at that point thereafter saying something happened here and do something different. In Hotspot, you had to recompile, but there was no long-term cost to loading that method. It went away after the next round of getting. And I can go into like fine details with people like IBM and I went around this back and forth a dozen times. Self-modifying code. Hard, but you're going to do a lot of it, so get it right. Code patching, inline caches and non-intrant code. Okay, so what is an inline cache? Let me fill people on that one. So an inline cache makes a virtual call as cheap as a static call. So you look at Hotspot, you look at all the virtual calls. In C++, you say virtual, you get a virtual call. In Java, you don't say virtual, you get a virtual call, unless you say final. Well, no one says final, so they're all virtual. Okay, well, in practice, none of them are actually overloaded, and you can prove it. And so you get a static call from the JIT point of view, and you can inline them like it's happening we just talked about that case. Okay, but if you can't prove it, it turns out that most call sites that you can't prove aren't going to go to multiple targets. In practice, do not. They only go to one target. So you want a one-entry cache. An inline cache is a one-entry cache saying, what is the class of the object I have in my hand? If it's this class, then I'm going to go to the JIT code for the one method that he would have as his implementation for that class. So the inline cache is a one-entry key-value pair. The key is the class, and the value is the call. And the implementation is compare the class ID to what I expect it to be. If it is, make a static call to the target. So that's a load compare, branch never taken. The load misses often in your L1 cache because you're loading your object header. You don't need it for any other reason. The compare is predictable. The branch is predictable because you never fail in inline cache. So you make a static call. So in x86, all I have to issue the load, it'll resolve when it does. Predict the branch, take the call, all done in like 2 clock cycles. So an inline cache makes what would be a painful load, jump register kind of operation turn into something that's a couple of clock cycles long. Same cost, almost the same cost as a non-virtual call. Statically, the set of call sites that you didn't inline, you can generally, you put an inline cache in, roughly 95% of them, the inline cache will forever only go to one target for the entire lifetime of the program. The other 5% will flip, going megamorphic right away, and they are actually going to some bushy set of possible choices, and they have to do a load, jump register. So you can go do all kinds of, I mean, I've done a billion instruction traces left and right. It's a really good problem, just a really good solution to the problem of endless virtual calls. So when you get it wrong, you have to patch it. Or actually, in the beginning, you start with inline cache being empty, and it misses because you've got no class. You don't know what class is going to show up there. So you have to patch it from empty to a holding class, and you have to patch the call to the correct target. And you have to do it in the face of racing Java threads who are multiple running through here and multiple guys trying to patch. And it has to be legit for any running Java thread to see any partial patch. In particular, on the x86, the iCache, dcache rules are completely loosey-goosey. So any partial patch in whatever order, never mind what I do for fences of any kind, he can see on the other side of the line, like completely independently. So every possible partial patch has to be a legitimate x86 instruction that does something sensible. And that's a tricky barrier. So to get that right, you have to think through what these caches look like, and then you want to get yourself some support so you don't have to think about it anymore. You can say, oh, stick an inline cache here and have it work right. You obviously still have to do iCache shoot down for everybody, but x86 has these variable size things. You want to update something in memory that the processors, another core is trying to read and do. You have to do an atomic update, otherwise you get cache shearing effects. Atomic updates cannot span a cache line, so you have to know that the patchable portion of the instruction isn't crossing the cache line boundary. So for instance, a call instruction is 1 byte, but the offset is 4 byte offset, and I want to patch it. I can patch in between these two, but I can't patch in between these two because if it spans a cache line, he'll get a partial patch. And some racing Java thread will see half of the patch and half of the other address and crash and burn. So an actual inline cache is like load, compare against a constant, is the right class, branch, no, it was good, and call. And I can patch here, I need to patch here and here, and I can slide this thing around as long as I don't have a cache boundary crossing the patchable pieces. So I insert some knobs to make it slide around. But getting that right is a pain in the butt, and you want to get it right once and like pickle it down somewhere. To do that, we use a high-level assembler because there's lots of hand assembly going on, and it gets lots of runtime support. You want a lot of VM invariants and integration. Like I mentioned before, I want to take this inline cache and shove it around with knobs until it doesn't span a cache line boundary. That's very x86 specific. The RISC world does it a different way. Fine. Normal assemblers don't get that kind of support. Furthermore, when I found that inline cache and I put it down, wherever it landed, I want to record, here's a program counter address in the code because that points to some JITted code that I can't let go away. I can't recycle that memory because some processor is going to grab that instruction and go there at some future date. So I need to track that. I need to track that place. So this is metadata. So I'm recording metadata with my assembler. I have an OOP. I have a class ID. I have a class pointer saying, this is the class I expect here. Well, garbage collector moves that class. He has to update that pointer. So I have to have a new pointer here somehow. So there's metadata referring to these things. So you record all kinds of cool metadata stuff with all your invariants that you're proving. And you want to write like assembly because you're actually intending to write assembly, machine code. So you write something that looks like assembly but is actually valid, C code, Java code, whatever. When you run it, it just emits the code into a buffer, proves all your invariants, supports all your, collects all your metadata, shoves it off to the side. Like, I wrote all this code to a buffer. It's x86, so that I have to do a relocation. I'm going to pick it up and move it somewhere when I'm done. At the act of picking it up and moving it, all fixed addresses have to be updated. All relative pointers to things outside that scope have to be updated. All that's handled by the assembler for me. There's a lot of fun games in that high-level assembler that make it easy to write assembly in support of the VM. Hotspot's been running with a double word header, even on a 64 VM. One of the things we did at Azul, we pounded it down to 1 word, which is this large, interesting memory savings. It's every object got 1 word shorter. How many objects do you have? Well, it's a lot. The real question is how many objects fit in your caches? Well, now about 10% more. And on x86, performance is all how fast can I run from one cache miss to the next. If I get 10% more stuff crammed in my cache, I run 10% faster. It's like pretty fucking linear. So I can't use a 64-bit class pointer because obviously that eats the whole word. So I need some dense class ID. We pick like 19 bits of class IDs, and we have a table mapping classes to class IDs, and there's a bunch of hacks and similar to deal with that. You need a thread ID. I'll talk more about those in a minute. That's for your locking. You need a hash code. Actually, in a 64-bit LAN of 200 gigabyte Java heaps, you actually want all 32 bits of hash code. It's a significant savings when I have a few billion objects that I don't have so many collisions in my hash tables. Then thread ID, what I did was I took all my stacks and I aligned them on 2 meg boundaries. And then if I want a stack pointer, I just mask off the lower bits. So to get the thread local storage area, I take my stack pointer and I move it to a jump register and I mask. That's a short mask because I only need to knock off however many bits. And then I got a thread local storage pointer, and instead if I moved it and shifted it, I got a thread ID. I use thread IDs for object headers for locking. I use a lot of coordinate VM code starts by hitting the thread pointer and then do something. So that happens all the time on the fast path. So this has to be fast for your fast path, or your fast path being fast. Because they're aligned, I can do TLD games for page protection. We do that for underflow and overflow protection. Stack overflows in Java have to be done synchronously at exact boundaries. So you march along and you're recursively actually extending your stack endlessly. You fall over some 4K boundary that flips a bit. I say, oh, now run forward to a safe point. So I have to guarantee during the time you touch a new piece of stack and the next safe point you don't touch more than 4K more or you'll double stack fault and blow out. So that was a JIT job to make that happen right. But then you unprotect that page and have another one behind it to catch them when you have bugs. And you get to run out a little bit, hit a safe point, and then start throwing your stack overflow exceptions to get on your stack. So getting stack overflow, underflow drove a lot of interesting, difficult runtime behaviors here. Getting that correct and cheap. You don't have to check your stack pointer on entry every method, which I have seen people do. This one has no cost on entry and exit, but instead there's a lot of runtime costs around page protection games. Safe point pooling, single threads. This is a key performance hack for having the VM work well with a huge count of threads. We get to a thread level storage, it's my TLS there, by taking a stack pointer and masking a little bit, and a little bit of bytes, and then reaching out and grab a pointer, word from memory. If it's 0, I'm done. So it's an L1 caching load, predictable branch. It's like 1 clock cycle in x86. If the bit's set and want to do something, usually I do a lot of self-service tasks. Here's some of them. I'll crawl my own stack for finding GC roots and reporting them, or do a GC face flip. I'm just going to flip some bit in all the pointers. I might get told to install an exception. So one thread can tell another thread, here's a thread.def for you. And you have to take it at a known Java execution point. So let's say point. And then begin throwing an exception. Might get a bias lock revocation where somebody asks you, hey dude, you actually got this locked, and you're just like speculatively holding on to it. And then that thread has to decide, if he's at a point where they might go or not. Debuggers, IntelliJ, you get a breakpoint in running code, it stops. What did it do? Well, what it really did is it took that running thread and it deopted it on the spot. It set a safe point bit, it ran to a safe point, it deopted from that safe point to an interpreter. Now the interpreter has a hook saying, oh, I'm talking to JVTI, I want to let you debug me. So you totally get optimized full speed to the code and also debuggability. A theme that people have talked about in the 80s and 90s, and Hotspot does it. This is how. Clean up your inline caches. Your inline caches have a class pointer and a target and a call. Inline caches can go stale because maybe the thing you're calling had to get invalidated because you loaded a new piece of code and you had this jitted assumption about no overloading of some non-final method that got wrong. That code is crap, shouldn't be executed anymore. Here's an inline cache pointing to it. Somebody passes an inline cache, they jump there. You got to fix that. So you have to go tell that inline cache, no, don't do that anymore. Right? Or maybe you've got a class you're going to unload. And the only thing holding on to it is inline cache. You got to go into that inline cache and clean the class pointer out and say, no. No one's making any of these things anymore. There's no of these things. GC wants to get rid of it. So you have to go find your inline caches. You can't do it while you're running, or you'll crawl over that inline cache with a running thread. So he stops at a safe point and says, wait a second, let me go clean my inline cache out. Cooperative preemption I already mentioned. Has to do with OS trying to stop 100,000 threads while it's here. Okay. Things I won't do again. Things I did that in hindsight sucked. Okay, I did this thing in C++. Wow, it was a painful thing. Java would do it, nearly everything I did in C++, I could do in Java now. In particular, in C++ land, a lot of the C++ objects are floating around, doubled up as objects in your object heap. And then your this pointer was actually a garbage collectible pointer. So you have some pile of C++ code, you're talking about member variables left and right. You make some function call, who knows why it dies. Well, it runs off and calls something, calls something, calls something. Way down here in the stack, God knows where, you block for whatever, and a GC cycle happened. Where your this pointer up here just moved. You're in your C++ code, your this pointer is now somewhere else. Next time you take a virtual call, you go through the this pointer, which is stale, you grab the wrong thing, you grab the next register out, you jump to it, and you're running some random crappy code, God knows where in the universe, and you run another 100 instructions and you die. And what the hell happened? Unwind from that, find that bug. Oh my God, what a pain in the neck. Also, there was like a dozen, Hotspot actually had about 10 at one point, roll your own versions of GC, malloc, stack obs, region, arenas, there's a lot of names for these things. But they all have the same effect of, I'm going to allocate something out of this fixed buffer, and then I'm going to reset the buffer and go again. It's a version of GC. Use GC. C2, that's the heavyweight compiler, is using Burr-style pattern matching. That was useful when you had VAXes. Never needed on RISC, that was the point of RISCs. And then never needed on x86. If you look at an x86 now, the architecture state is actually very regular. Whereas, the encodings suck. They're horrible for encoding. That's the simplest problem to deal with. The actual architected instruction set is pretty damn regular. So you don't need this fancy instruction pattern matching, and it adds this extra level of indirection to JIT engineering. I would never do that again. Just emit the obvious instructions in the obvious way, because there's only one obvious choice at any given point. That's the trick there. Patch and roll forward save points. The original Hotspot did this. Another nightmare. It started out looking good. You decided you're going to stop somebody by stopping them instead of polling, because we were worried about polling costs back in the day. The stop thread's not at a save point. Once you got his address, like the OS didn't lie to you in the first place, you then had to move him forward. Well, the thing we tried to do was patch all the save points with breakpoint instructions, and then tell the OS, let this guy run again. And he'll have a save point before he exits the method, hopefully. We didn't miss any spot with Jet. Okay, we hit a save point after a while. A breakpoint was good. Somebody else was running, couldn't handle the breakpoints, so they were fetching breakpoints were in the middle of inline caches because you're about to make a function call. You had to stop that. So the guy trying to patch inline caches would discover a breakpoint where he thought there was an inline cache, and he'd get all confused. So then you with two pieces of code. One was patched, one was not. So there's duplicate code put around, so you patch one, not the other. Totally non-trivial patches, pain in the butt. Multiple OSs spin resume cycles to get the guy to roll forward to save point. Never, ever do it again. Do polling. Generic poly-save registers. So it sounds like a great idea, and for people who have lots of registers and no registered windows, it is a performance thing. Like PowerPC and ARM have a lot of registers and no registered windows, and they want to use generic poly-save registers. So they want to have a bunch of things that are live across the call site. Well, the caller doesn't know what's in them. He just says, I want these registers, I'll spill them and load them later. Well, he spills them on stack somewhere, loads them later. Now, deep in the call stack somewhere, you take a GC cycle, you call your stack. You ask this frame, hey, give me your oops. He says, well, here's my oops, but I got these registers from the caller that I didn't know what they were. I saved them here, but I don't know what they are. So we have to go up one more. I got this pile of registers, I've been mapping what the caller, from the stack to the, ask that guy, hey, what are these? And he says, well, this one was my oop, but those I got from the guy above me. I don't know what they are either. Go. These stack calls are a real mess. So, don't bother. x86 doesn't need them. It's not an end of the world if you get the right allocation good to live without them. It does help some, but not a huge amount. Register windows, on the other hand, both the fixed and the variable size, all seem to work fine. Once we got that stack frame, next frame, iterator thing figured out, having register windows was no big deal. The only tricks were around knowing when you had flushed them and when they had wanted to reload. The hardware was constantly trying to reload them, so you had to have one final flush of them before you unlock for GC or whatever. But that was all done below on a stack iterator level.
So I noticed I was talking to Peter Kessler, and he told me multi-threading, when that came out, became the final death knell for register windows.
It was difficult to get right. We eventually got it right on Spark, and then I did it on Titanium, and then I did it with Zool, and so by that time I had it kind of wired in how to make it work right. It was a pain in the butt, because multi-threading meant there was a GC thread running separately from the guy running, and it was exactly what I was talking about. you had to have some final register flushes in the right places when you did the handoff between a running thread waking up from he went to sleep in the OS and just randomly woke up just as the cycle was about to end. So the GC wants to probe that last new update and then release this guy. And this guy's already running, and so he's already got his hardware prefetcher going, and the hardware prefetcher has already fetched out stale bits. Then the GC says, okay, I slap down the release of the lock. This guy Kazes wins the lock, immediately goes. Hardware has already prefetched the wrong things, and then he grabs the wrong things and dies. So you had to get it right. You had to get the flush in there at the right point. That was because of multi-threading, GC background GC. Good. But we got it worked out originally. It just took a while. Didn't understand there was a problem there in the beginning, right? It wasn't obvious that this could happen to you. In hindsight, oh, it's blazing odds. In foresight, no one saw it coming. Adapter frames versus frame adapters. What the hell do I mean? An adapter frame that left a frame on the stack. And that meant that going into some Java call to some native call, I pushed a frame and I scribbled with registers and I did handles and crap. And when I unwound, I had an opportunity, because there was a frame on the stack, I had an opportunity to unwind. In particular, I could move things from one return register to another. That's sort of the useful thing out of it. The downside for adapter frames when you're calling Java to Java to Java was that you had a spare frame on the stack and it screwed up all kinds of stack calls. In particular, there were some pathological cases where you ended up with an infinite number of them unwinding. I went from this mode to the interpreted mode, or I went from the interpreted back to the JITted mode, I went from the JITted to the interpreted, and you get like an infinite number of them. Frame adapters, what I mean is they adapt from frame to frame, but they don't make a frame. As a frame adapter is a adjective, and that meant I shuffle args, but I don't actually put a frame on the stack. So I don't. When I crawl the stack, there is not a spot where I say this is a frame that is not a Java frame, it's not a native frame, it's an adapter frame, and that doesn't happen anymore. Okay, so that one works, but this one does not. We tried it a bunch of different times. We needed it for intercalling between native code, interpreted code and JITted code. And eventually I got this right at Azul, and I didn't have to do this anymore, and I got rid of it when I was all happy. Things I want to do again, constant loops in the code, looks really great on x86, it's a 32-bit immediate when you're in a 32-bit JIT, because you can load them in one instruction. Hey, I need a constant loop, I got a string pointer. I'm going to load hello world, I'm going to load the string for hello world. Ah, okay, I got a loop, great. And then, of course, when you went to other machines, you didn't have 32-bit immediates because they didn't have variable length instructions. They had 32-bit instructions. You can't jam 32-bit immediate and a 32-bit instruction because that's all your bits, right? So they had multiple instructions. They had to split the damn thing around. And that meant when you wanted to move it, you had to go patch it. You had to go patch it in all these places. You had to patch it atomically. For a running thread would get half of one patch loop and half of another. And then you had to stop all your threads, and that required to stop the world pause in your GC where you otherwise didn't need one. So, yeah, better answer, just put them in a table, and you just load them from a table. And instead, the load instruction has, the table index in it. Load table base, constant table base plus offset. Easy to schedule around the JIT. It's a one-cycle load that's going to hit in cache, and we know what it does. Now the loops are just like laid out in table, just like a big array. Concurrent GC just modifies them as it does any big old array in memory. Fewer instructions on all other VMs except x86. And then, of course, no tracking in the code of where the loop is, because it's in some table. Locked object headers in the stack. This is Hotspot's original thin locks. They picked the object header out of the object, and they would jam it in the stack as a way to count recursion with unary counting. That's 1, 2, 3, 4, 5 counting, and 5, 4, 3, 2, 1 when you unwound the stack. Okay, sound kinds of nice. But it turns out that your object header was not in your object. It was on the stack somewhere. And that meant everyone else who went to go grab your object header had to have a screw around where they said, am I looking at an object header, or am I looking at some forward reference pointer to some stack where the thing actually is, right? And maybe that other guy is in the middle having his stack repacked because he's de-opting, and all his JITted frames are being thrown away and turned into interpreted frames. And so his stack is getting shuffled. So where is it in his stack? Well, it's getting moved. Whatever. So the answer was a pain in the neck. We're doing all kinds of things. And so don't do it. Leave enough bits in your header that you can count, 0, 1, 2, many. That's all you need. Once you get past like 3 bits, you're done for, and the lock is deeply recursive, and you go slow path. But people don't necessarily take the same lock a super high count of times. right? So you can have a short counter in there, and after nesting a few times, you're done. You know, it didn't overflow, or it did, went slow path, you didn't care because it didn't happen in practice. Okay. So that was an hour and a half. I have another talk that's just as long. Follows immediately after this one is why you can't throw away code, or what it takes to throw away code. Instead, I'll just top this one off, and we'll go to Q&A for a while. So really, the high-level picture here is you're going to run any kind of code, including native code. Run it well, run it fast, run it defensively. Meaning the native code can block or do horrible things to GC. Handle extremes of threading to do high good volume GC, concurrent parallel GC. Have lots and lots of code that you're going to deal with. You get all these general purpose trade-offs that are cheap and easy if you own the whole stack and are actually really hard when you're trying to be general purpose. A bunch of open questions I have for the big JVMs. I can argue strongly both ways on graph coding versus linear scan. As I mentioned, it's kind of a slippery slope. Linear scan is easy to get started with. So graph coding has ultimate performance. I'll claim that this one's answered. I like what we did with the one-word VM. There's some serious engineering hacks to squeeze it down to one word, but they're worth it. I'll also claim that Hotspot lived forever and a day with an interpreter and a heavyweight jet, or an interpreter and a lightweight jet. And they should have gone to a stage 1 medium weight, lightweight jet with profiling a long, long time ago. And I don't know about a stage 0 jet versus an interpreter. That one's kind of open. Like I said, I can argue fairly convincingly both ways. OS threads versus green threads, or hold your own, whatever, these are threads. Again, I can kind of argue both ways. Ultimately, Hotspot started out with green threads and went to OS threads. That seemed to have worked out okay. But Java threads are known to be fairly heavyweight, and they're like the Dudley fork join framework is all about making thread-like objects extremely lightweight by sidestepping threads, because Java threads are too expensive. Right? Okay. High throughput versus low pause GC. Those are both interesting, and it's hard to get both. Zool got both, but they completely changed how GC works. Everyone else seems to pick one or the other, and they get most of the other side, but not peak on the other side. So you kind of have to, there's some interesting trade-offs there, and a lot of engineering goes in there. Okay, I'll claim done for the moment, and back up to, your whatever, and Q&A.
Thanks, Clive. That was great. You've read a bunch of papers. You've got a bunch of interesting stuff. How about it?
Yeah.
What is the quickest path to a working parallel concurrent GC?
Parallel concurrent. So the answer is there's no quick path, but there's a quicker and slower path. There's a lot of papers out on the Azul GC, and they open source bits of it in the past. I pioneered doing that one myself, but I'm very familiar with it. And I know that it can be made to work relatively straightforwardly. Hand in hand with that GC is what you're doing with code generation and how it interacts with GC. And that's another set of decisions that I went through here that have to be thought through and dealt with. You're talking about from scratch then? Yeah. It's not for the faint heart here. So in particular, there's a lot of OS level games. User mode TLB handler gets installed, and you're screwed with the TLB directly. You have to rob bits out of pointers that you're mirroring in TLB to hide them, and then there's all the there's no point to it. How about this? Unless you're already fairly highly performant elsewhere, right? The parallel concurrent collector is important when you're running lots of threads and they're running fast. So they're producing garbage fast. If you're writing, you're putting together some initial system from scratch, and you're saying, one thread, or sort of very fixed thread pools, doing some straight up run something in parallel and shut down. You're probably not producing garbage at a high volume, and you probably don't need a low concurrent collector. No point in concurrent collectors is low pause, right? But when you start to say, yes, I routinely have 100 threads, they're routinely producing gigabytes a second, and I want to keep my pauses down. I guess what I'm saying is an academic exercise, I would do it as an exercise, but don't have your research, your PhD, getting that done. Not worth it. Yeah.
You first.
You've described a whole bunch of decisions that have sort of interactions, sometimes unanticipated and so forth. So when one starts designing a system, obviously there are some rules, some things are good, some things are bad, but is there sort of an order in which to think about making some of these decisions? Start with GC or make those decisions later?
So no, up level your head, why? So is your decision I'm getting out of grad school or not? So that's one set of decisions right there. So if the answer is I'm doing this for academic research, totally different price point, right? If the answer is you're working for Oracle and you're going to say, I'm going to outdo Hotspot, I'm going to start over, clean slate it, and outdo Hotspot, you have a different set of choices you're going to make, right? You're over at Nokia, you're Ericsson, you want a better VM for your phone, you got a different set of choices to make. So go from that level, then come down from there and say, where am I going to go? From there, you'll decide, do I have a JIT or not? If I'm having a JIT, am I going to have multiple tiers or not? Am I having an interpreter or not? You must have either an interpreter or a JIT. But you can skip the interpreter if you play the game right. Decide right now that one, because that drives a lot of things that follow. Then start with the basic, I'm going to have a GC or not. If you are going to have a GC, it's conservative or exact. And if it's going to be exact, decide concurrent or not, as opposed to parallel or not. There are things in GC that are more straightforward to parallelize and less straightforward. And the other piece is, am I going for low pause or high throughput? And both is tougher than one or the other. But if you're just looking at my cell phone, I want low pause. I don't care for high throughput. I got 1 to 2 cores producing garbage. I can collect with one. I don't need to have a parallel collector. And maybe you want a concurrent one. Then with that GC go read barrier based, which is what Azul did, versus write barrier based. That completely changes the set of algorithms that are possible. And make that choice up front because that's going to drive it. Azul did it with a read barrier, which I believe made it much easier to get a low pause thing. The write barrier ones have slightly higher performance and are very straightforward to implement a parallel throughput collector, which is a blocking stop the world, but very quick to collect and then go again. But very quick, maybe not good for a cell phone conversation. You decide where your price point is there. And that's sort of big ticket items. I mean, you've already said I'm in a virtual machine. I'm going to run something that's not machine instructions. So I've got a bytecode somehow. It'd be nice if you could dictate the bytecode. So bytecode's stack oriented because that was a pain in the butt to work around. It led to a lot of decisions on the interpreter that was painful. If you get to define your own bytecodes, go to register style bytecodes. Then you can make fixed frames that the interpreter can live with and the JIT code can also live with, instead of this variable frame hack, which led to all kinds of grief with frame adapters. Then again, your native code, you're going to live with the calling convention on the native code. If you do, you can skip a lot of the frame adapter crap. That's a lower performance point in general, but not always. Some of the DSP guys, GPU guys, don't have to worry about var args. And so they blow it off and they say, hey, floats and float registers, it's all good, right? So those are kind of, I think that's a lesser choice. I think primary up front, what's your business reason for doing this? Get out of grad school, go make go make JavaScript Killer 2.0, go make whatever, Dart or Go for my internal core engineering that might go viral and it might not. Right, like set myself up to go fast if I want to, but start with the low-end versions of everything, and then work your way forward from there.
Yeah. So there's a lot of stuff in here that's weird interactions with architecture, memory models, weird interactions with the OS. How much do you think the OS design choices impacted the VM design choices? And in ways that were just like a pain in the ass, but at the end of the day, it's just as fast, and things that like fundamentally change the way you do it. Like, I might be faster if I had a really trivial OS that just gave me all the cores and then got out of the way.
Are you talking about OS or are you talking about x86 processor choice?
OS.
Okay, so OSs come with, hardware these days comes with virtual memory protection. It doesn't have to, and DSPs and GPUs don't. So ask that question. If you have that, then getting that support out of the OS enabled a bunch of fun games.
ability to do TLB management, read and write locked pages, and in the case of GC, force the TLB to mirror physical memory so that I can hide a bit in a pointer. Those are things I wanted. Things that I wanted to get that didn't get: reliable stack pointer program counter. Dan OS is doing the context switch, damn it. Get it right. And the answer was mostly. But one time in 100,000, it would blow, and we get a call from the president of Deutsche Bank screaming at us that they were not going to renew their Sun contract for $10 million annually until we root cause what went wrong with this damn thing. Okay. Getting tons. One of the things I have another talk where I talk about crap I want out of OS that I don't have. A millisecond time accuracy. There are most large Java web server kind of guys, application servers, have a hidden dependency that system.current time millis is clock cycle monotonically increasing. So what the hell do I mean by that? I mean, on this thread, if I get the current time millis and I store it down in memory, that thread will see it be exactly equal to his or greater. They will not be off by even one clock cycle. But the time from when I get it to where this guy can get it passing through memory is probably measured in 4 or 5 clocks if it's L1, L2 hits until all handshakes go right. So those two clock numbers for current time millis have to be cycle accurate on these two cores, however that's done. So in the beginning, that was originally done by Linux going down to some NNTP kernel crap call, God knows, it was very expensive. Then along comes SpecJDB, which as a benchmark did current time millis 1 billion times a second. Like, holy crap. So that had to get faster. So people immediately started grabbing for solutions, how to get that faster. And the answer then followed after some quick hacks were done that it broke everybody who was more complicated than SpecJDB benchmark because they didn't expect time to go backwards on them. And the breakage were always a weird, bad, some horrible transactional thing they were trying to accomplish, like failed and aborted and died in bizarre ways, what the hell. So to get that cycle accurate and to get it right, there's something totally trivial to do in OS and extremely hard to do in user land. The OS needs to have a page which is read-only, it can write to, and no one else can read it, and just once a millisecond it bumps the counter. Everyone just goes to this fixed address in memory, loads the damn value out, that's your current time millis, you're done. So the cost to compute it from a user land is a load, right? And it's clock cycle accurate across the board because the hardware will just make it accurate as it gets bumped. So this is like, there's a trivial fix in the OS for this. The thing that people did is they went for the x86 read TSC counter register, which in the beginning was not clock cycle accurate between two different cores. And so you'd load up this one, you load up that one, and they'd be off by a bunch. And we tried that for milliseconds, but it was all over the map. So it's even a spec that Nanotime will use that, and it will be screwed up. Then the x86 got it where it was monotonically the same, except when hardware heat throttling kicked in, and they would slow a core down because it was either looking idle or it was too hot. But they wouldn't slow them all down, and then they get off from each other again, which is just as bad as before. And then it was not clock cycle accurate on a multi-core box, multi-socket box, because these two guys wouldn't handshake and keep it in sync as they went. Something we did do at Azul and paid a big price for that, but it was totally worth it, because if you could rely on that damn thing being clock cycle accurate across the box, it made your life so much easier. I like that out of the OS. As I mentioned, I did my stacks. I aligned them on 2 meg boundaries so that I could use a fat TLB to cover it, or I could use 4K TLBs to protect ends for overflow and underflow protection. And an overflow, I would have to free up a page and let you run on a little while to hit a safe point without falling off the next page. And in low memory, it was always readable because that was my thread level storage. And I had a lot of things for fiddling with thread level storage on a regular basis. Turns out we have a very high speed, high quality profiler doing random stack sampling that we jammed those stack sample bits in the low 8K. So we moved the base and stack pointer up a little ways for that. And that's a ring buffer that just like jams stack pointer, stack traces down at high volume. And the trick with that one is all profilers that don't do a random stack sample, which is all safe point-based profilers, all lie exactly where you need them the most. They all lie in that anytime you have they don't count profile ticks at safe points. But the JIT tries very hard to throw out all safe points out of hot, small loops. because that overhead slows that loop down. So hot, tight loops don't have safe points. Therefore, they get no profiling ticks. So you go look at your kit and you run some stupid hot loop, you'll get no ticks where you want them the most, where you expect to see them the most, like it just lies. And this is a well-known problem across all, you go find academic papers talking about it. You have to have real stack sampling. Then you have to call your stack reliably, which eventually got straight out of the Zool, and Sun still had issues. And then you had to record those stack traces somewhere that a profiling thread would scrape that buffer and haul off to the side, hang on to it, and then a profiler tool could go pull them out and like pretty quickly. I'm playing with TLPs around stacks. What else am I getting out of the OS that I cared for that mattered? Oh, Fairlox.
Which OS did you use Azul boxes?
On the original Azul hardware box, it was all from scratch. We got some core Linux designers in, a couple of them that were actually really good guys.
Okay. Did you get what you wanted that way?
Oh yeah. We got what we wanted out of the OS. And then we went and pushed some of that back into the Red Hat distro. And some of it we figured out how to do without, or we just paid the price. Like the SafePoint game was done in hardware on Azul side for free, and we just paid the price on x86, but he's all fat and wildly out of order, and L1 cache hit is essentially free because you're blocked waiting on some other miss to main memory somewhere down the line. You're running cache miss to cache miss. So that was all like nothing. I could go pull that talk out. I could do that here in a minute. And we could go, what other things? Are you doing the OS land here? Are you doing OS stuff? Yeah. Fairlox.
I'm just thinking about like model mismatches. Is the model the OS thinks about, because the OS is abstracting the hardware, it's giving you some view of the hardware. Is there a fundamental mismatch between that and what you want to do? Or because all these are sort of like little things that could conceivably be embedded in any sort of OS, right? None of these are, except for maybe the exposing the memory, virtual memory stuff. Most of them are not really fundamental to an OS's perspective on things. They're all just like little.
No.
Little
So I want to run. I mean, I've lived with this classic OSs for 20 years, right? So we all kind of worked out how it fits in that model. What would you do differently that you might think would be turnable into something useful out of the OS? So the abstraction, I can't use hardware bits because it's Java and that's the mantra is you're going to run everywhere and the hardware's not possible to go there. If you did say, I'll let you scribble with the hardware bits, but in a way that's safe for running programs. So I still want virtual memory, I want OS level protection, that whatever stupid thing I do, I don't bring the box down. If you're willing to give them on that, then there's some different games you want to play. You actually want peek and poke operators, so people will write device drivers in Java or whatever the hell. If you're not going to give them on that, but you had some abstraction for handing out low-level things, I don't know what you would do that probably would fit into what's in the, what you could do now in a VM. I'm looking for interesting things. So bigger ticket items, threads and Fairlox. We still want threads, still want OS level protected threads. Oh, thread priorities, that's a good one. That's on my list, I should pull it out. Linux has no thread priorities unless you're root, and no sane IT guy will let you install anything as root. So there are no thread priorities. So you can't tell the JIT to run at a higher priority than the non-JIT threads. So if the benchmark launches 1,000 threads on your 8-way box and they all do something stupid really fast in the interpreter, and they all flip the counter at once and they say, go JIT, there's 1,001 threads, one the JIT. The rest of them are all running the interpreter waiting for the JIT to complete, who never gets a clock cycle. So he never actually JITs code, so you run an interpreter the entire time. So you want thread priorities within a JVM to do support routines. So concurrent GC only works if you actually have CPU cycles spare for the GC to run, same as the JET. So those guys, VM support routines run at a higher priority than Java threads. And then the Java threads want to have some priorities within themselves, and they don't have any mechanism for that other than whacking the whole VM up or down with nice. If they whack it with nice, they lose to the other VM or mice wheels running on the same box or the Hadoop or whatever the hell, right? They can't get an edge in sideways. So that was a Linux fail that they don't have thread priorities other than root.
So,
No, go.
So my understanding is Zuul's on custom hardware where they added their own instructions. So how does that how does that compare to something where you have an Intel chip that's highly optimized and have lots of research and time put into it versus like a custom chip.
Right,
Like,
exactly. So that's the Azul thing, and I was at that company for a long time. It was really fun, and I'm glad I did it, but it was sort of doomed, you know. When the chip first came out, it had 24 cores when an x86 had 2, and they were 4 times slower, and you had 24 of them. So the end result was like hugely faster than an x86. We could stack them in a box up to 16 sockets. So we would have a box that was 100 times faster than we could get out of an x86, but each thread was 4 times as slow. Turns out that programming model is hard to do. Even with Java doing all the good things it did with threading and you know, concurrent library, this and that, it was hard for people to write parallel at that level scale unless it was very regular supercomputer style parallelism. Irregular parallelism at that scale was difficult for people to do. So, you know, it was too narrow a model where it really shined. The thing that it did well was it ran GC and JITting in the background with all those cores. And it really, you know, at that time, the GC performance was unheard of. We would have you know, hundreds of gigabytes of heap with tens of gigs of second allocation and take no pause longer than a few milliseconds. And that was just completely, you know, well beyond what you get out of any x86. And so we sold to people who needed that kind of GC performance. And there were a couple of market spaces where you know, retail apps doing web services, Kohl's and Fry's and you know, Walmart, anyone who's got, Target's got a web face, they're selling, Black Friday hits and their load spikes to the roof. And Azul blocks will just have enough extra threads. It's all done with thread pool stuff. That would all just scale up endlessly and not pause. And other solutions would typically, you know, go black on them during their peak load time, crash under load, whatever, and they would lose some huge amount of money. So we talked to these people about their amount of sales, and you know, some of these companies were selling like half their annual sales came on Black Friday weekend. So that they would, you know, they're a $500 million a year company, $250 million comes out in one weekend. So if their server went down that weekend, they were just like, and we sold to them, but there's not that many of those guys, right? So it was just too narrow. We got it faster, but not as fast as x86 got faster. And then everyone fought multiple cores, and we were sort of forerunners and took a lot of, you know, arrows in the back that the next guys, you know, x86 just stepped over our bodies and went on and said, oh, that's how you do that. Okay. You know, that problem's hard. We won't do that one. And oh, you can solve this one this way. And then they learned, and you know, we took the bullet. Yeah, like I said, it was fun. I'm glad I did it. Won't do it again. You access it.
The millisecond clock page idea.
Yeah.
I like that. Has anybody done that? I don't think it could be cacheable. You'd have to mark it as uncacheable.
No, you want it cacheable. It caches all the normal ways. Because when the hardware takes the write from the OS, you know, the OS updates it by writing it, the hardware will just invalidate the caches and reload the new
Okay,
write.
so you're assuming that the hardware will
Yeah.
across all processes.
Yeah. In the way the hardware normally does. Like everyone will see this version, or they'll see the next
So
plus one version.
Has anybody ever implemented that?
We asked for it, and I don't think we got it. The Linux get time of day clock got better. It's currently similar. They have a series of words that you have to read twice to see that they don't update atomically. You read them once, then you read them a second time. If they didn't change, then you got an atomic snapshot. Then you compute current time notice from that with some adds and some multiplies and divides. It's not too bad. So it's 20, 40 clock cycles instead of one. It's okay. I mean, I think that's what happened to that. Where like it didn't matter enough to bother Linux kernel team like screwing with it. But they went to that version. They didn't have it when we started. They went to that version, I don't know, somewhere along the way. But they were trying to get Linux normal, whatever OS C time or whatever the damn thing is. There's some structure you get. And that structure was exactly the one C programs expect. So the go load it call was all inlined by the C compilers to load these four, compare again, they're good, I'm done, right?
A lot of the complexity in your slides come from threading, it seems, and specifically from shared memory threading.
It's the only kind there is.
Right. Do you foresee a future where you have a pure message-based model and
No.
it's all distributed memory?
No.
Is that a red herring?
Because you can't do everything you can. And in particular, you can't go implement your actors in actors. It's, go self-host yourself, right? I have a very different coding style I use when I'm looking for high performance stuff. And I go to state machine coding. I didn't talk about that here at all, but it is clearly the balls to walls fastest way to go if you can handle the sort of complexity. I don't have any tools to help, so it kind of sucks. I always manage it. So I'm not claiming it's for everyone, but it's how I implement all kinds of fun games under the hood in VMs. I end up doing a lot of that. If you look up click non-blocking hash map, that hash map is linearly scalable to roughly 1,000 cores, the big as Zolbox had, with any ratio of reads and writes, which is completely not true of all other hash maps. It's a concurrent hash map, but it's completely linearly scalable for 1,000 cores, and I'd go more if I had more, and I believe we retain linear scalability. That's a state machine programming model. I have the current survival mat is doing clustered computing. We have a Java memory model that's cache coherent across a cluster of machines using message passing between machines because that's all you got, you have network packets. But we're as fast as anyone out there with a distributed key value store, and also we're exact consistency, which we're doing with a state machine model under the hood. So I basically had a long talk with Kevin Normal, who's a hardware cache designer, did Azul's caches on their 1,000-way machine, did Sun's early caches for their Spark 123. I had a long talk with him about hardware cache coherency models. They're all state machines. I did a state machine cache coherency hardware style protocol. And as a consequence, I have a distributed key value store that's as fast as the fastest one out there, but exact consistency as well. And we're not selling it. It's all open source. It's free. Go get it. But that's state machine. So it's a different coding style. What I'm doing what I built with those tools is I built a MapReduce framework, which programmers write stuff in an obviously parallel way for data sets that are massive and have an obvious data parallelism built into them. And they just need a MapReduce paradigm that's sort of faster than the standard Hadoop one. So they're theoretically clean, nice, very pretty, pure Java. You can write almost anything you want in Java, and I'll make it parallel distributed, but it's because it's a MapReduce paradigm. That's sort of an easy way to get big, fast, broad parallelism. To make that run, I'm using Dudley's fork join, which is another variant of a parallel programming model that has a little more complexity to it. And having said that, I'll go to the next path and say we're using the counted completer version of fork join, which is essentially continuation passing style, like Node.js. And I would love to have more support for that in the language, because I think that is a way that will let you build all your multi-threaded coherency things on top of other stuff, code to it directly, and be sort of a reasonable paradigm for talking about something when you can't do essentially bulk synchronous parallel. Now, MapReduce is bulk synchronous parallel. It's do this thing on everybody, and when you're done, do this next thing on everybody, and you're done. Okay, fine. If you want more complexity than that, there's actors as an obvious choice, and fork join with continuation passing style is another different paradigm that's higher performance than actors, and I don't claim it's better or worse yet. I haven't figured that out, but it's something that we're trying now.
We should probably call it quits. At least give these guys a break. Any last high urgent questions?
I'll be here for a little while yet.
So I mean, it sounded like with your 1,000 core system, or you were talking a lot about how like the OS would come in and like interrupt some threads. So why didn't you like explore like one thread per hardware core and then just do like a mini green thread to like instead of?
We were porting Hotspot, which didn't do green threads anymore.
Okay.
So we used OS threads, but the OS was ours to play with. So it was a very lightweight threading model in the actual OS. It wasn't Linux.
Right. But I mean, like you were depending on the OS to interrupt your threads. You could have had like preempted, like cooperative.
No, you must, or you have to be perfect in your jitting. So it's especially on the x86. You have fewer cores. You have lots of runnables. You have to be fair. What do you do to make somebody else run when this guy's not giving it up? How do you get him to give it up? Well, if you don't do cooperative self-suspension, you have to preempt him, and that requires an OS. There has to be somebody who actually has the rights to tell another thread, stop now, you can't run no more, get off that core, that's for somebody else. So that's an OS. I mean, mostly defines what an OS does. That and virtual memory is like the main things to get out of OS. The cooperative thing was a statistically good answer, but not a perfect answer. So statistically good meant nearly always on my 100,000 runnables, all of them were stopped at a safe point. So I could crawl their stacks and screw with them with GCs almost always, but not 100% perfect. To be perfect, I would have to have the time between when a polling point was passed and when the time quantum ran out and the OS had to say, you're being a bad boy, I'm going to kick you, had to not be long, right? Or else you wouldn't get off the core in timely fashion and somebody would starve. So that one would require the JIT to perfectly put where safe points went. Instead, the JIT went for the minimal number of safe points that covered all paths. And that meant there was a time from when one safe point to the next that was not being tracked by the JIT and could get fairly large. I said there were no safe points in hot loops, but when that happened, he would unroll and jam, but you would still get many thousands of instructions then between the unrolled inner hot loop before he'd exit that, take a safe point check, and then go right back in. And so, was that too long? I don't know. If it was too long, if you had to restart it and let it run to a safe point in order to do a GC. But statistically, it didn't happen all that often. You routinely ran into native code that was going to run for a long time. Go to labs routine. It's doing matrix multiply. It's going to be here for minutes. Okay, you want that core back, to be fair. You must preempt it. There's no cooperation there. I went and grabbed some Fortran library. I compiled with a Fortran compiler. It is not got no safe points in it, right? So I just have to have preemption out of the OS.
Okay. Thank you again. 10 minutes. Feel free to stick around if you want, or if you want to head off and
Until I find my kids.
Okay.
There's nothing special.
All right. Let's take 45 minutes to get back onto sort of the normal pace of things. It's like you got the whole course compressed into 90 minutes.
Okay, we're done.
Okay, so today I'm going to start on optimization stuff, and it's going to run for a good few hours, so we'll only get a start on it today. There'll be more coming next week. And a lot of this should fill out much of the terminology that Cliff used in his talk, so if there were things there that you found mystifying, hopefully they'll be less mystifying by the time we're done. Okay, so I'm going to start by talking about dispatch optimizations, mainly because the early history of VMs was intimately tied with dynamic object-oriented languages. And the dominant performance feature there, the biggest impediment to performance is dispatch. And so there was a lot of effort paid to making them fast, which it turns out laid the ground for work that followed later, which is probably even more significant than just the merely dispatch optimization. But if you've got an object-oriented language that's doing dynamic dispatch, so the first thing you have to do is make that stuff fast, or ideally remove it entirely before you can move on to the next thing. So we'll start there. Inline caches you've already read about and heard about. I'm just going to give you a recap just to make sure that that's all clear, because that will lay the groundwork for the generalization of inline caches and then the use of those generalized structures to gather profile information, which is how we get to adaptive optimization, which will be next week. Okay, so the idea is 20 odd, 30 odd years old, and it works on this observation that we use the last invocation of a method call as the predictor for the next, and in the original Dodge-Schiffman technique, you embed that prediction in the code by calling the thing that you called last time. So I've got the movie version of inline caches here done in animation, which hopefully will make everything very, very clean. We'll run this twice, one in its slightly simplified form, and then I'll show you some of the bells and whistles. Okay, so we start off with the call site for the invocation that we're trying to optimize. So that's a p.f in Java or a pf in Smalltalk or Self. I assume our compiler has put the target of the call in a register, and it's, in this case, has put the name of the thing we're calling in another register. So the F is the name or a symbol or a string or a reference to those. And in the initial case, when the compiler generates code, he just binds the site to a generalized lookup routine. So the first time through, we call the lookup routine. This is our program counter, the red thing that's going to move through our code. Hop over to lookup, and then what do we do when we get there? Well, the first thing we do is we find the thing that we're actually going to call, and that's obviously based on the semantics of the language and the lookup algorithm. So that's a call off. And that will result in an end method pointer to the thing that we're going to call, if necessary, generating the code for that method if it hasn't been generated before along the way. So we now have our end method that is the thing we want to call. And the next step in the lookup is that we patch the call site to link to the entry point of this this method. So that arrow that used to call lookup now points to the entry point of the end method, and we've had to change the address in the call sequence to point to that. And now, having done the patch, we can jump to the end method. Now we jump in a little bit after the beginning to something called the verified entry point, which bypasses the check that's part of the inline cache. So you'll see there's basically, I'm writing in kind of mock assembler there, two labels, entry point and verified entry point. Usually there's a fixed offset between those two, so it's easy to compute the verified entry point. So we end up now running the rest of the method. Now next time we run through, we hit the call site, we're up here, we call down, and we go into the regular entry point, and the regular entry point is going to check whether the class of the receiver that we've been given in the register is the same as the class of this code, which in this case is P. And if it isn't, then we go back to running the lookup. Otherwise, we carry on running the rest of the end method. So let's assume that this time misses, and we go back to lookup. Lookup's going to use the name and the receiver type to generate, a new method, or find a new method. It's going to do the patch and relabel the call, and then jump to the verified entry point. And basically, the movie runs over and over again with as many arrows and targets as there are different call targets. Now, as I said, there's a slight glossing over there in that the way I structured it was that I was passing the name of the thing we were calling in one of the registers. Well, that's only needed by lookup. Once you're actually running, you don't really need the name anymore. And so there's a common trick that's applied here, which is to reuse the register which we used to pass the name the first time to pass the class or some other key that we're going to use for lookup the next time around. And an easy way to do that is just to reserve a slot at the call site, a data slot, which contains the lookup key, and just load that on the way into the call. So let's have a look at the way it looks now. So in this case, we have the call site. After the call to lookup, there's a data slot, which the return sequence for the end method will have to hop over because there's not an instruction, there's just a data word. And when we start, that data slot points to the name of the thing we're trying to call. So the calling sequence loads that thing into a register and then calls lookup. Lookup now has the name of the thing in R, and it has the receiver register by some convention containing the thing that we're invoking the method on. It's now going to use that name and data pair to do the lookup and the code generation as before. It's going to patch, in this case, the call and it's going to patch the call to point to the end method, which is this part, but it's also going to write a data word into that X slot, which points now to the class of the type that this method came from. So next time around, if it matches the exact same class, then we're done, we have a hit, and if it doesn't, we have a miss. So it does the patch, jumps to the verified entry point, and off we go. Next time through, if we call, we get to the entry point, we do the test of the class, which is usually a single load off the receiver register. If that doesn't match P, then we call into a little prologue into the lookup routine, which is going to find the name of the method that we're trying to look up and put that in the register so that now the lookup routine can be reused as it was before. So that's just a little prologue that adds a little bit of code to the beginning. So we go here now. Finding the name of the caller is pretty straightforward because we just came from a method who knows its own name. That's somewhere in the data structure, and then we put that in R. We find the end method, generate the code if necessary, and off we go and do the patch of the receiver type, the receiver class, and the call and off, and all is good. Hopefully straightforward. Yeah. Okay, so the effectiveness was the question.
I probably just about to talk about it now.
Okay, so this scheme works well if and only if we're not bouncing between lots of methods all the time, right? And it's just an observation of most people's programming style that doesn't happen that often. Most calls are monomorphic, meaning that they call the same thing every time, or they're occasionally polymorphic, that they call a different thing, but the change isn't very often. However, you do find, that's not the case always, and we'll look at the solution to that in the next technique. Now, the polymorphism, when it oscillates between two or more sites, obviously the thing that matters is how often the oscillation takes place, not how often the calls are. So if you have something that ping-pongs between two targets and alternates, that's going to perform very, very differently from a program in which you call the first guy for half the program and then the second guy for the other half, because you've only got one change of inline cache there, whereas it's the other one you've got a change for every call. It used to be the accepted wisdom that this structure was faster than a vtable lookup, and I think Cliff just said that. I'm not sure that's true anymore. You'd have to really, I haven't seen any studies done on contemporary hardware to see what the branch predictors are like. If you have a good branch target buffer here, there's no reason it couldn't just predict where that call is going, in a vtable, and do just as well, and sort of have the loads sort of figure it out afterwards and sync up. But for the longest time, this was faster than doing a vtable lookup. So you could actually get dynamic languages doing calls faster than they were done in virtual calls in C++. And as you just saw, code patching, especially in a concurrent environment, is tricky. I'm not going to go down that particular rat hole here. If we have time later, then we'll discuss it. Or you could, watch the video of Cliff and slow it down. See what he said about that, because that's basically the gist of it is, there's all of this detail that you have to get right, and the hardware generally is not making your life any easier. So the generalization of this technique is the polymorphic inline cache, and that's to deal with the cases where you've got genuine polymorphism in the call side, and the inline cache is performing very badly because you're ping-ponging between two different end methods, which is really slow. And that happens in real programs. So if you imagine the inner loop of a drawing program and it's drawing stuff on the screen, you have circles and squares and text and arcs and stuff. Well, each of those is going to be a different method, and they come in sort of random order on the screen. You can't tell the user, please draw your circles first, and then draw all your arcs second, and you'll find it's faster. It doesn't really work. So, the original inception of this technique was to deal with that performance problem, but you'll see next week that it actually gives us a solution to a completely different problem as well as we go along. And so the idea here is that we're going to do the single inline cache thing to begin with. Here's the picture before the first call, where we have the binding to the lookup routine. We call the lookup routine, that rebinds us to the end method that's found first time around. But then when we miss the second time around, instead we generate a little piece of code, a dynamically generated stub, which is going to do two type tests. It's going to test against the first thing we saw, and if it was that, then it's going to branch to that end method, and then it's going to test against the second thing we saw, and if it's that, it's going to branch to that method. And if it's neither of those two, then we go to the miss case and do the full lookup again. And if we go down the miss case and do the full lookup again, we generate another one of these things and extend it. Usually you can't extend them in place because of the way memory is fragmented and stuff. So usually you make a new one and you patch the call to point to the new one. And this kind of just goes on. So, I got bored of drawing arrows, so this one I drew a box, but I didn't put all the arrows in. But you can see how this kind of generalizes, so that sort of deals with, you get to the obvious question, which is, well, how far do you go with this? Do you just keep making this bigger and bigger and bigger and bigger? Well, no, you don't really want to do that. You've got some choices here. You've got, once you reach some kind of predetermined size, you want to switch to a different strategy. In the literature, that predetermined size is known as megamorphism. You've got many, many different call targets, and they're actually actively being used. You can do a couple of things. One is you could just bind to a more generalized routine that has a non-site specific behavior, so a global method cache. We saw that 4 or 5 weeks ago, a simple hash table based on the receiver types and the selectors. There's all sorts of other tweaks too. As the thing grows, linear test might not be the optimal sequence. You can reorder the tests as you generate the new stuff to put the most frequent case at the beginning. If you have frequency information, we'll see how you get that next week. And you can even sort of go to a logarithmic search structure by doing a branching tree if you really want to. And that gives you a bit more scale in the technique before you have to fall back to a V-table. And just to remind you, here was the picture from a few weeks ago of the V-table structure. And the idea here is that we have, for each class, a fixed offset from the class pointer. There's a list of entry points. And so the sequence for a call here is, given this pointer in your hand, you get the associated class, then you do an index based on some coloring of this table that was computed at compile time, and then you call off to the target method. This works well in a statically typed language. We can't do it in a dynamically typed language because you don't know the set of things that might be called. So this is a good fallback for a statically typed system. And as Cliff said, even in Hotspot, which is statically typed, it only does this after the inline caches have failed to be effective, and it uses the inline caches and the polymorphic inline caches to gather the type information and the profile information it needs for the optimizing compilation. We'll see how that works next week. Okay, so that's one technique for optimizing calls. Another completely different one is to deal with the problem of primitive types in a dynamic language. So you've got this problem that you see an A plus B, and the A plus B might be an integer add, but you don't know because you've got no type information whether it's going to be a string concatenation or integer add or some other completely different thing. But integer adds are cheap, and so you want to make that case quick when it is an integer add if you possibly can. And so the solution is to speculate in the compilation. You just kind of assume that the overhead for doing the add case is very low. You guess that it's going to be that one, and you test that guess. And if it isn't, then you do the more general one. So you've made the more general case a little bit slower, but only a couple of instructions slower. And you've made the adds a lot quicker by not doing a full lookup. Even the inline cache is kind of punitive to do addition via a call and a return. So here's an example. Our source is simple, A plus B. We end up generating code that kind of looks like this. This is sort of pseudo C and assembler blended together as more C-like. So we're going to test whether our two operands are tagged integers, and if we are, we just do the addition right there and then. And this is all done in line in the code emitted by the JIT compiler. Otherwise, then we do the full general dispatch, which might be an inline cache, which then has its own fallbacks, as you've seen through polymorphic inline caching or global method lookups. And this was the technique that was done in the Deutsche Schiffmann system. In Smalltalk 80, there's a bytecode that says, I am sending a plus. Okay, you don't know that that's going to be an integer plus, but what the compiler did was it said, I think it's probably going to be an integer plus. I'm going to emit this code in line to do these tests and the full lookup otherwise, and that's how it's going to work. And even though when you browse in the Smalltalk system, you could find the source code for the plus operation, which meant, give you the illusion that you could change it changing it had no effect because it didn't change what the compiler generated. Right? The compiler always generated this for pluses. So it was kind of baked into the JIT that plus was, at least on integers, always going to be integer addition. We'll see next week how that was generalized in self so that plus could be anything. And it would do the right thing when you changed it. But that's a sort of a shortcut that was a reasonable thing to do. In general, programmers don't feel that upset if they can't change what plus does. Some might, but tough luck. Right? This is you get a faster system and it's relatively tractable to build a compiler. That's a sort of an instance of a more general pattern, which we'll see over and over, which is fast path, slow path design. I've used these terms a lot already, but just kind of to put them in a picture, what we're really doing is we're looking for some feature of our implementation which has a skewed distribution. It's not 50-50, or if there's 5 choices, that they're not all 20% probability. Something seems to be more likely than the alternatives. And what we're going to do is look at the common case and try and make it faster and, if necessary, at the price of making the uncommon cases slower, although there's a balance to be had there. So this picture sort of depicts that. We're going to make the fast path inline and generate code for it, and the slow path will be when we generate code will probably be a layout of line call, and that we'll see as generalizes into a number of tricks later on. So the next technique is one that I might have mentioned, but we haven't looked at in any detail, and that's called customization. So the idea here is, if you look at a standard compiler, a C or a Fortran compiler, especially something from 20 years ago, it sees a piece of source code, it generates a piece of machine code that is, its best attempt at generating the code for that particular source. But there's no reason a priori why you can't generate multiple different instances of the machine code tailored to the properties of the call site if you really wanted to. It's just no one ever did that before. But once you get into an object-oriented language, then it turns out that that's a really good idea. It actually gives you a lot of opportunities for optimization that were closed before because of the nature of the language. So all we have to do is decide when to do that and what we're going to customize on to make it work really well. And there's a paper from 1989 by Dave Unger and his student at the time, Craig Chambers, that showed how to do that in the context of self. But it's a fairly general approach that works for pretty much every object-oriented language. So the idea is that within a method in an object-oriented language, a large fraction of the invocations are going to be on self or this. They're going to be recursive on that type at least. But if you look at the way inheritance works on most languages, you don't know that type ahead of time. You know the class that the method is embedded in, but it could be executing in the context of a descendant type, a subclass or something. So what we're going to do in this approach is we're going to generate the code for one specific point in the hierarchy and say only applies to that point. So if I have a class of a particular flavor, then I'm going to make a method that works only on that and that doesn't work on its subclasses. In the past, before this paper, everybody just reused the same code in all the subclasses because that seemed like the right thing to do. But you'll see we gain some optimization. So here's an example. Suppose we have an abstract class of 2D points with 2 concrete subclasses for the polar and Cartesian representation. I'm going to use kind of self-like notation here, just because it's concise. So I have a Cartesian point with a parent slot P that points to point, which is at the bottom. And the Cartesian point has an x and a y, and an R method which does the Pythagorean thing to figure out the hippopotamus. And then the polar point just has a R and theta representation, but inherits from the same abstract class. And in the abstract class, in point, I've just got one thing, which is tell me the length of the hypotenuse, the R. So what can we get from this? Well, when we first invoke that print thing on a polar point, then we know the thing is a polar point, and we can generate code in the context of that polar point that assumes, for example, that the R is right there and we know the field offset in the object. We don't need to go through all of the method dispatches, and when we generate the code for the Cartesian point, then we know the method that would have called and just bind to it directly. So we can generate different methods for the different cases, and all we've got to do is make sure we install them in the lookup system such that we never get confused. We always call the right method for the right thing, and that includes if we extend the class hierarchy later, we can't necessarily reuse the generated code. So, for example, if you make a descendant of the polar point and you change R to not be a stored thing but a computed thing, then you can't call the thing that's looking at the stored attribute anymore. So pictorially, here's the sort of the self-like picture of the objects and their methods. So there's the class at the top, which has its print R method and the two descendants. When we call print R on the Cartesian thing, then instead of doing a lookup to find R, well, we know R is right there. We can determine that, and we can just call it directly, or even potentially inline it if we really wanted to. We'll get to that in the next part. When we call print R on the polar point, then we know R is right there, and we know it's a data slot, so we can just load it. We don't have to do a full dispatch. So we've got a number of advantages here. The red things are meant to be kind of end methods. They don't really get installed in the objects. They're really the meta system that manages the code cache behind. So it's more complex than it appears here, but still manageable. And they're not replacing source methods, right? They're end methods. They're not visible to the end user. And then when if we call R from this guy, then again, we can install a copy of that code in the map of the class for the Cartesian point that knows directly where the slots are that have to be looked up, and we can align the dispatches on those axes. So you can actually drive this a lot further, and we'll see after we've got to inlining that you can get a lot of mileage out of this. So the pros of this approach, the pro is that you can eliminate an awful lot of dispatches if you kind of apply this repeatedly, and that improves performance, but at the cost of generating more code. And the danger is that if you have a large hierarchy with something inherited but not redefined, that's used in a large fraction of that hierarchy, you can end up with generating an awful lot of copies of the same system. And in fact, Self was, the early version was terrible for this. In that graphic environment, for example, there's a hierarchy of graphical objects, which I think has 100 different types in it. And so you'd end up, after you've been running the environment for a while, with the abstract methods that came from the top of that hierarchy. There'd be 100 copies of the machine code, and they're all exactly the same, because it was just applying the code generation blindly. It wasn't doing anything to say, well, this actually would be the same piece of code as I got last time, so why not just share the machine code instead of regenerating? So it has to be used with a little bit of caution.
So in terms of these inline caches, roughly what percentage of the L1 cache or maybe L2 cache would you dedicate toward code generation?
Sure, I could have thought that in those terms. You mean of the generated code?
No. Let's say I'm running my interpreter and I'm generating code. How much? I need to allocate some amount of space in order to for a cache. How large should that cache be?
Oh, you mean how much space should be made for the generated code? Well, that really depends on your memory footprint and what kind of applications you think you're going to run. Some systems just say, well, that's a user problem. Right? You could pass me a flag and tell me how much you want to dedicate, which kind of is a cop-out, because generally speaking, users have no idea how big their code is going to be. But 10% of memory is not a bad number to begin with. Depends. If you're on a very small system, it might be half a memory, where because the data that you're manipulating are really small relative to the program. But as the system gets bigger, usually the data size grows much faster than the code. So by the time you get up to servers, it's probably more like 1%. The thing that's easy about this is, if you have a settable size, it's easy to know when it gets full, because at that point, the system either dies or it has to do some flushing of code or compaction, and at that point you can record that fact and say, ooh, maybe next time you want to make it bigger.
I thought there might be some analytical thing. It's already been done for common programs.
I can't think of one. There might be, but I can't think of it if there is one. Okay. So another technique in optimization that follows from that slow path, fast path thing is to identify that some directions of a branch might be extraordinarily infrequent. So infrequent that you can do something hideously painful when you go down that path, because you're not going to do it very often, if at all. And so an example of this is an exception handler. You might make the assumption that exceptions are exceptional, and therefore you're going to penalize the cost of the exception handling to improve the cost of everything else. And so there are a variety of strategies. One is you can just sort of pessimize things down that path relative to the other path, preferentially allocate registers down the line variables of the other path, or make the control flow drop through on the fast path but go out of line for the slow path, that kind of thing. But there's a more drastic technique, which is, just don't even compile that code, right? If you think it's never going to run, just don't generate the code at all, and instead put in a stub there that's going to call the compiler and say, oh, we were wrong, we actually came down here, it's time to generate code, or transition to the interpreter or something down that path. And if you do that, then one of the things you find in a system like Smalltalk or Self is that they're actually incredibly frequent, these uncommon paths in generating code. And so having a sequence of instructions and a call and all of that stuff, it takes a lot of space. There's a cheaper way of doing that, which is most instruction sets have a single trap instruction, and some opportunity to write a user level trap handler that will catch that, and often it's like a 1 word or a 1 byte or 2 byte instruction. You just plunk that in there, and then the trap handler kind of has to figure out what happened. I came in here, where did I come from? I have a return PC. I have to look back at that to figure out which method I was in. I have to figure out what I was doing at the time, what was live, restore all of that stuff. There's a lot of complexity down that path to making that work, and a lot of time. But if it's genuinely uncommon, then it's probably a win. And so the idea is we take our slow path, fast path diagram, and we just, chop off that side, right? We're not even going to fall through. We're going to call out into some other world which is going to handle the situation from there, and it's not going to fall down through the merge point and execute the code afterwards. And that's really important, because now the code after the merge point doesn't have to deal with anything other than the conditions that were true down this path. So, if you came in here because you thought something was an int, well, now you know it's an int, right? There's no question. There isn't a merge that in one case it was, in one it wasn't. Now you know it's an int, and you can assume that throughout the rest of the method. And that's also a very powerful optimization technique in combination with the others. So here's an example in a RISC type architecture where you're doing an addition on a pair of oops and you want to test. You're assuming that both oops are going to be an int. So in this case, I'm assuming the 2 least significant bits are 0. I'm going to do the test and a branch and test and a branch. And if those pan out, then I'm going to do the addition. Otherwise, I bail out. And it's up to the runtime system at that point to figure out, what I should have been doing and do that. And you have to, the compiler, when it emits this, is going to have to either emit code or have a convention in which you could figure out where you were and what you were doing at that moment, because there are going to be lots of these traps, and it could be any one of them that's going into the trap handler. So to transition, there's going to be some kind of trampoline, and the trap handler is going to have to say, okay, I'm in an uncommon trap. I came from this place. I have to retrieve, figure out which method I was in. I have to figure out what was live and where it was. I have to probably generate a stack frame that looks like an interpreter frame and populate all of those things. If your JIT code is already dealing with a separate stack, then a lot of that is already done for you because you're not necessarily executing in a very different environment. But if you're doing register allocation, then the values are in registers perhaps and not in stack locations, and you're going to have to figure that out from the breadcrumbs that the compiler left behind. You're also going to have to change the compiler so that it can generate the continuation of this method if that's the way you're going to run it, or generate the whole method with an entry point at this point so you can translate into it, transition into it, or you run in the interpreter. That's a choice that's available. Okay, and the last thing we'll look at today is splitting. So the idea here is we have pair of branches that are both still reasonably likely, so we can't eliminate one of them. We want to we want to be able to generate code from both of them. But they divide the world into cases which are so different that there's no point in having a common piece of code after the merge point. We might as well duplicate the code after the merge point and customize it based on the assumption from the test. So looking at the picture, we have this thing again. In this case, I've got sort of a blob representing the following code, and what we're going to do is we're going to duplicate that code and customize it based on what we know now from the test. So if the test says variable x is of type t, in this piece of code I can assume x is of type t and just compile with that assumption. And in this one I know it's not of type t. I can generate the converse case. And what you find is if you do this and you apply it repeatedly at places where you would do, for example, primitive handling, then you can break out the part of the method that represents the integer interpretation entirely from the part that represents the non-integer interpretation, and maybe even just uncommon code that out. So this is the kind of thing that a compiler would be doing on its IR. It would be making passes over its IR, looking for cases like this, and then doing the cloning of the subgraphs and the manipulation of them. There's a nice example which I'll run through, but I don't have time really today to go through it. So next week we'll look at kind of an example where we blend all of these with inlining and see how far we can get with compilation using these techniques, and then we'll look at blending inline caches and picks with counts so that we get profile information and look at tiered compilation. That's where we have a second or third level of compilation doing more optimization. Any questions on that?
Yes, so all these optimizations that you just described, what are the factors that a compiler takes into account in order to decide whether or not it should do these? I mean,
So there's two ways of doing this. When the original customization paper was written, the techniques were described initially, the compiler applied heuristics. It said, I'm going to guess that it's going to do it this way, and I'm going to make this assumption and do a transformation. And it would make these repeated assumptions and transformations. And if it got it right, you won big time. If you got it wrong, it was hopeless. You got this long compile pause with a piece of code that actually didn't do the right thing when you ran it, and you just had to immediately throw it away and generate it again. What we'll see next week is a framework for putting the decisions in place by gathering type and frequency profiles using counters, both in methods and also on inline caches. And when you run the code with that in place, then you get very accurate profile information, and not just frequency information that says I've been here many times, but it can take a call site and split it into all of the different type cases that have occurred with basically a histogram of the types. And now you have really good information on which to base your inlining decisions and your other optimization decisions, assuming, and this is, I should always say this, assuming the past is a predictor of the future. That's always the assumption here. The past predicts the future. If that's not true, you lose big time. But that's the answer. We'll look at that more next week. Okay? Thank you.
Just in time,
compiler assignment has finally been written. Posted it last night. You have 3 weeks to do this one.
Oh.
Compared to 1 week for the tag limited optimization. The difficulty is not proportional to the length of time you have to work on it. It's much more difficult. Be very careful. I didn't exhaustively detail how to use 6, but I do tell you what instructions I use, and I expect everyone to just know how to use it. That's it.
Do you have one more project after this?
Sorry?
Have fun with that. One more project after this?
Yeah,
Yeah, go screw yourself, Nathan.
You should team up with this guy. But not that one.
No, I already had some partners.
I'm like, haven't done anything this semester, so I should probably do research. Or like,
You better get figure out an exchange and not do that.
yeah, I should just pass trading lines.
Are you not? Are you seriously that good? Like checks?
Well, but for me, passing is B+.
You have to use plus or
Thanks, so yeah.
It's pretty cool. It sounds like a
That's bullshit.
It's like
Because it's to satisfy a requirement.
I guess
Like,
the fact I was thinking
I think you have to get a B+ in all shit.
Yeah, I don't remember
Never graduated. Good. Do you have a question?
Now we have like
gel.
Before
we solve all the bugs.
So isn't one little, why is it ended up?
Because once you do this, if you can find someone else,
Yeah.
We have all these checks.
like I don't and like this next week is just
it's
totally
very
fun.
straightforward change.
They're actual
What?
I have 2 weeks
statements and not like that's
This
But
next
it's
week.
not like
See.
Is it
is it
flag? It's just like
ouch.
Yeah,
It's
so
really
it's
good.
super great. But I use
Oh, that's rough.
Yeah, you just jump on it.
I will.
Sorry, you're asking.
yeah, that's the
So, like,
yeah,
the reason
that's-
like
that-
Just log in.
yeah, exactly. But it'd be so much easier
For future.
future.
Although a gel plus 4 could be used to.
Okay, so there's two. Sorry,
Yeah.
there's 2 parts to your question. The first question was, are we just simply allocating a buffer and generate instructions?
Everything in italics
Right.
is just
If
explaining.
we are, what's
like
the
a
justification of static
Not enough of them,
Right. So the answer to that is,
Right.
it basically
Yeah,
is a
so I
static
Yeah, but
buffer.
they everything's gonna test this.
Your
I just want to create like a barrel.
If you do this,
Or is
then
it
right?
afterwards,
Or is it like
you
debug
can
as
choose
the next
not to
argument?
generate
Like it's-
something
You're right.
entire
I do like tests.
You can choose
It
to do
Yeah,
it.
it's just like
And there are more
like
yeah.
it's like bash or you
Your jig is not finished after this.
Yeah, you have to.
separates the mistakes.
Okay, makes sense.
Yeah.
How can I throw in like a cache?
No, I would just throw in
Hey.
space debug and test it that string.